Hello, and welcome to Easy Drift Sleep. To support our quiet corner of calm, please consider liking this story and subscribing for future peaceful escapes. Welcome, traveler, to a quiet journey, a gentle exploration into the very fabric of understanding, a descent into the profound depths of knowledge itself. Tonight, we embark upon a voyage through the vast and intricate landscape of science, a realm where curiosity guides every step and discovery illuminates the path. Imagine a world woven from inquiry, where every question unfurls a new vista, and every answer reveals another layer of wonder. This is the world of science, a systematic enterprise that meticulously builds and organizes knowledge, crafting testable explanations and predictions about the universe we inhabit. The very word science carries with it an ancient echo, stemming from the Latin scientia, a term that simply means knowledge. Yet within that single word lies a universe of endeavor, a continuous evolving process of seeking, observing, and understanding. It is not merely a collection of facts, but a dynamic method, a way of thinking that has shaped our perception of reality for millennia. From the earliest stargazers to the most advanced particle physicists, the human spirit of inquiry has driven this relentless pursuit, pushing the boundaries of what is known and venturing into the territories of the unknown. At the heart of this grand enterprise lies a framework, often referred to as the scientific method. This method is not a rigid, unyielding set of steps, but rather a flexible and iterative cycle, a dance between observation and deduction, between hypothesis and experimentation. It begins with careful observation, noticing patterns, anomalies, or phenomena that spark a question. Why does the apple fall? How do stars shine? What causes disease? These initial sparks of curiosity ignite the entire process. Once a question is formed, a scientist proposes a hypothesis, a testable explanation, an educated guess about the answer. This hypothesis must be precise enough to allow for investigation, a crucial characteristic that distinguishes scientific inquiry from mere speculation. The next phase involves experimentation, or systematic observation, designed to test the hypothesis. This might involve controlled laboratory experiments, extensive field studies, or the meticulous collection of data from natural phenomena. The goal is to gather empirical evidence, information derived from sensory experience and observation, which forms the bedrock of scientific understanding. After data is collected, it is rigorously analyzed, often employing mathematical and statistical tools to identify trends, relationships, and significant findings. Finally, based on this analysis, a conclusion is drawn, either supporting or refuting the initial hypothesis. The scientific method is rarely a linear path from A to B. It is a cyclical process, where the conclusions from one experiment frequently lead to new questions, prompting further research and refinement. A hypothesis might be partially supported, leading to modifications and new experiments. It might be entirely refuted, compelling scientists to formulate entirely new hypotheses. This constant revision and refinement of theories is a hallmark of science, ensuring that understanding evolves as new data and technologies become available. Science continually refines and updates its understanding of the world, always based on the latest evidence and discoveries. This inherent adaptability is one of its greatest strengths. A crucial concept within this framework is falsifiability, a criterion brought to prominence by the philosopher Karl Popper. For a theory to be truly scientific, it must be capable of being proven false. This means there must be a conceivable observation or experiment that could demonstrate the theory to be incorrect. If a theory cannot, in principle, be disproven, then it falls outside the realm of science. This principle encourages skepticism and critical thinking, urging scientists to actively seek out ways to challenge their own assumptions and theories. It distinguishes scientific claims from non-scientific ones, providing a vital filter for knowledge. Empiricism, another core tenet, emphasizes that knowledge is derived from sensory experience and observation. It grounds scientific understanding in the tangible world, moving beyond abstract reasoning alone. Through careful observation and measurement, scientists build a picture of reality that is verifiable and reproducible. This emphasis on evidence and reason is what makes science such a powerful tool for understanding the natural world, allowing us to build a collective body of knowledge that is constantly tested, validated, and expanded. Science is fundamentally about asking questions and systematically seeking answers through evidence and reason, a continuous, unfolding narrative of discovery. As we grasp the foundational approach of science, this systematic way of knowing, we can begin to appreciate the grand scales of the universe it seeks to comprehend. From the meticulous observation of a falling leaf to the profound contemplation of distant galaxies, the scientific method provides the lens through which we attempt to make sense of everything. It is a journey that begins with the very small, the fundamental particles, and extends to the incomprehensibly vast, the cosmic tapestry itself. Let us now gently turn our gaze upward, beyond the familiar confines of our world, into the boundless expanse of the cosmos. Here, astronomy, the scientific study of celestial objects and phenomena, takes center stage. It is a discipline that has captivated humanity for millennia, inspiring awe and wonder, and pushing the boundaries of our understanding of existence itself. The night sky, a canvas of twinkling lights, has always invited questions. What are those distant points of light? How far away are they? What is their origin, and what is their destiny? Modern astronomy, equipped with powerful telescopes and sophisticated instruments, has begun to unravel some of these ancient mysteries. One of the most profound and widely accepted theories describing the universe's earliest known periods is the Big Bang theory. This prevailing cosmological model suggests that the universe began as an extremely hot, dense point and has been expanding and cooling ever since. From this singular, unimaginably energetic event, all matter, energy, space, and time emerged. The universe is estimated to be approximately 13.8 billion years old, a number derived from meticulous observations of the expansion rate of the universe and the cosmic microwave background radiation, which is considered an echo of the Big Bang itself. The vastness of space holds countless wonders, and some of the most enigmatic are black holes. These are regions of space-time where gravity is so incredibly strong that nothing, not even light, can escape their grasp. They form from the remnants of massive stars that have collapsed under their own gravity, compressing an enormous amount of matter into an incredibly small volume. The concept of a black hole emerged first from theoretical physics, a mathematical prediction of Einstein's theory of general relativity, and was later confirmed by astronomical observations, such as the detection of X-rays emitted by matter falling into them, and more recently, direct imaging of their event horizons. Yet, despite our advancements, much of the universe remains shrouded in mystery. Two of the most perplexing concepts in modern cosmology are dark matter and dark energy. These are theoretical forms of matter and energy that are thought to make up the vast majority of the universe's mass and energy. Yet, they do not interact with light or other electromagnetic radiation, making them invisible to our telescopes. Dark matter is inferred from its gravitational effects on visible matter, influencing the rotation of galaxies and the clustering of galaxy clusters. Without it, galaxies would simply fly apart. Dark energy, on the other hand, is believed to be responsible for the accelerating expansion of the universe, a phenomenon discovered in the late 1990s. These concepts highlight that a significant portion of the universe remains unknown to science, driving new research and inspiring future generations of astronomers and physicists. The search for understanding extends beyond the composition of the universe to its very nature and purpose. The anthropic principle, a concept in cosmology, suggests that the fundamental constants of the universe are finely tuned for life. This idea proposes that if these constants, such as the strength of gravity, the mass of an electron, or the speed of light, were even slightly different, life as we know it would not be possible. This principle has strong implications for the search for extraterrestrial life and influences how scientists interpret cosmic observations, prompting questions about whether our universe is unique or if there might be a multitude of universes, each with different physical laws. One of the most transformative discoveries in astronomy in recent decades has been the detection of exoplanets, planets orbiting stars other than our Sun. For centuries, humanity wondered if other worlds existed beyond our solar system. Now, thanks to advanced telescopes and detection methods, we know that exoplanets are not only common, but incredibly diverse. Thousands have been discovered, ranging from gas giants larger than Jupiter to rocky worlds potentially similar to Earth. This discovery has revolutionized our understanding of planetary formation and the potential for life elsewhere in the cosmos, further fueling the search for biosignatures in the atmospheres of these distant worlds. The Big Bang Theory, as the prevailing cosmological model, continues to be refined and tested. It provides a coherent framework for understanding the universe from its earliest moments through its subsequent large-scale evolution. From the initial burst of energy to the formation of the first stars and galaxies, and eventually to the complex structures we observe today, the Big Bang Theory offers a scientific narrative for cosmic history. Scientists continue to gather data from distant galaxies, analyze the cosmic microwave background, and model the universe's evolution to test and strengthen this fundamental theory. As we contemplate these cosmic whispers, the grand scale of galaxies, the mystery of black holes, and the invisible forces of dark matter and dark energy, we begin to feel the immense scope of scientific inquiry. It is a journey that takes us from the infinitesimal to the infinite, constantly pushing the boundaries of human comprehension. Each discovery, each new piece of evidence, adds another brushstroke to the magnificent portrait of the universe that science is diligently painting. The very act of observing a distant galaxy, a light beam that has traveled for billions of years to reach our telescopes, is a profound connection to the past, a glimpse into the universe's youth. It reminds us that our understanding is always evolving, always deepening. The questions we ask today will lead to the discoveries of tomorrow, continuing this endless, fascinating descent into the heart of knowledge. From the vastness of space, where galaxies drift like luminous dust motes in an endless cosmic ocean, we now gently descend. Our journey takes us inward, past the swirling nebulae and the distant, ancient light of quasars, to the fundamental forces and particles that govern all matter. Imagine shrinking down past the scale of planets and stars, through the intricate structures of molecules, until we reach the very bedrock of existence. This is the realm of particle physics and quantum mechanics, where the rules of the everyday world begin to dissolve, replaced by a universe of probabilities and strange interconnected phenomena. This transition from the macrocosm to the microcosm is not a sudden leap, but a gradual, deliberate shift in perspective. Just as astronomy seeks to understand the grand architecture of the universe, particle physics endeavors to uncover its most basic building blocks. It is a quest for the ultimate constituents of reality, the fundamental particles and forces that give rise to everything we perceive. The journey inward reveals a world far more intricate and counterintuitive than our macroscopic experience suggests. A place where energy and matter are interchangeable, and where observation itself can alter reality. This deep dive into the fundamental nature of existence is another testament to the tireless, systematic inquiry that defines science, guiding us ever deeper into the heart of what is real. The journey inward reveals a world far more intricate and counterintuitive than our macroscopic experience suggests. A place where energy and matter are interchangeable, and where observation itself can alter reality. This deep dive into the fundamental nature of existence is another testament to the tireless, systematic inquiry that defines science, guiding us ever deeper into the heart of what is real. Tonight, we embark upon a different kind of descent, not into the subatomic, but into the very foundations of scientific thought itself. A journey through the historical currents that shaped our understanding, tracing the origins of inquiry from its earliest sparks. We begin not with complex equations or laboratory experiments, but with the quiet contemplation of the natural world, the initial stirrings of curiosity that precede any formal methodology. Imagine a time before telescopes or microscopes, before even the concept of a controlled experiment had fully formed. Humanity looked up at the stars, observed the changing seasons, and felt the earth beneath their feet, seeking patterns, searching for meaning. The earliest forms of scientific thinking were deeply intertwined with myth and religion, a way to explain the unexplainable. Ancient civilizations, from Mesopotamia to Egypt, developed sophisticated systems of observation. The Babylonians, for instance, were meticulous astronomers, charting the movements of celestial bodies with remarkable precision. Their cuneiform tablets record centuries of planetary positions, eclipses, and lunar cycles. These observations were primarily driven by astrological prognostication and religious ritual. Yet they laid a crucial groundwork. They demonstrated the power of systematic recording, the ability to predict future events based on past patterns, even if the underlying causes were attributed to divine will rather than physical laws. In ancient Egypt, practical knowledge flourished. The construction of the pyramids, for example, required an advanced understanding of geometry, engineering, and logistics. Their medical practices, though rudimentary by modern standards, included surgical procedures, the use of herbal remedies, and a detailed knowledge of human anatomy derived from mummification. The Edwin Smith Papyrus, dating back to around 1600 BCE, is a medical text describing surgical treatments for various injuries, demonstrating a systematic approach to diagnosis and prognosis that hints at empirical observation. It speaks of examining the patient, making a diagnosis, and then proposing a treatment, a sequence that resonates even today. However, it was in ancient Greece that a distinct shift began to occur, moving away from purely mythological explanations towards a more rational, philosophical inquiry into the nature of the cosmos. Thinkers like Thales of Miletus, often considered the first philosopher, proposed that water was the fundamental substance from which everything originated. While his specific theory was incorrect, his approach was revolutionary. He sought a natural explanation for natural phenomena, rather than attributing them solely to the whims of gods. Anaximander, his student, proposed an infinite, undefined substance as the origin, and famously suggested that life originated in the sea and evolved into land creatures. These early Ionian philosophers were pioneers in abstract thought, attempting to unify the diverse phenomena of the world under a single, rational principle. The Pythagoreans, a secretive brotherhood founded by Pythagoras, believed that numbers held the key to understanding the universe. They discovered the mathematical relationships in musical harmony, realizing that the ratios of string lengths produced consonant intervals. This was a profound insight, suggesting that the cosmos itself might be governed by elegant mathematical laws. Their focus on abstract mathematical principles as the underlying structure of reality profoundly influenced later scientific thought, particularly in astronomy and physics. The idea that the universe is fundamentally mathematical, rather than arbitrary, became a cornerstone of scientific inquiry. Plato, a towering figure in philosophy, emphasized the importance of abstract forms and ideas. He believed that the physical world we perceive is merely an imperfect reflection of a perfect, unchanging realm of forms. While this view might seem to de-emphasize empirical observation, his academy fostered rigorous logical thinking and mathematical study, which were essential for later scientific developments. His student, Aristotle, took a different path, becoming one of the most influential figures in the history of science. Aristotle was a prodigious observer and classifier. He meticulously studied biology, categorizing hundreds of species of animals, and developed a comprehensive system of logic that dominated Western thought for nearly 2 millennia. Aristotle's approach was empirical, meaning he based his conclusions on observation and experience, though his methods lacked the experimental rigor we associate with modern science. He developed theories of motion, cosmology, and biology that, while often incorrect in their specifics, were comprehensive attempts to explain the natural world through reasoned argument and systematic observation. For instance, his geocentric model of the universe, placing Earth at the center, was a logical deduction based on observable phenomena at the time, and it provided a coherent framework that persisted for centuries. His emphasis on classification and logical deduction laid important groundwork for future scientific endeavors. The Hellenistic period, following the conquests of Alexander the Great, saw the flourishing of scientific centers like the Library of Alexandria. Here, scholars like Euclid systematized geometry in his monumental work, The Elements, a textbook that remained foundational for over 2,000 years. Archimedes, a brilliant mathematician and engineer, made groundbreaking discoveries in mechanics, hydrostatics, and mathematics. He formulated the principle of buoyancy, invented ingenious war machines, and developed methods for calculating areas and volumes that anticipated integral calculus. Eratosthenes, another Alexandrian scholar, famously calculated the circumference of the Earth with remarkable accuracy using simple geometry and observations of shadows. These achievements represent a pinnacle of ancient scientific inquiry, demonstrating both theoretical brilliance and practical application. However, with the decline of the Roman Empire and the onset of the Middle Ages in Europe, much of this classical knowledge was lost or preserved only in fragmented forms. The focus shifted towards theological interpretations of the world, and scientific inquiry while not entirely absent, was often subservient to religious doctrine. Yet during this period, the Islamic Golden Age emerged as a vibrant center of learning. Scholars in Baghdad, Cairo, and Cordoba preserved, translated, and expanded upon the works of Greek, Roman, Persian, and Indian thinkers. Thinkers like Al-Khwarizmi, whose work on algebra gave us the very word, introduced Hindu-Arabic numerals to the West, revolutionizing mathematics. Ibn al-Haytham, known in the West as Al-Hazan, made significant contributions to optics. His Book of Optics challenged ancient Greek theories of vision, proposing that light enters the eye, rather than being emitted from it. He conducted experiments with lenses, mirrors, and light, anticipating the scientific method by centuries. His work emphasized empirical observation and experimental verification, a crucial step towards modern science. Another towering figure was Avicenna, a Persian polymath who wrote extensively on medicine, philosophy, astronomy, and logic. His Canon of Medicine became a standard medical textbook in both the Islamic world and Europe for over 600 years, synthesizing Greek and Arabic medical knowledge and adding his own observations and clinical experience. These scholars not only preserved ancient wisdom, but actively built upon it, making original contributions that kept the flame of scientific inquiry alive during a period when it flickered in other parts of the world. In medieval Europe, the scholastic movement, while primarily theological, also fostered a revival of logical reasoning and systematic inquiry. Figures like Roger Bacon, a Franciscan friar in the 13th century, advocated for empirical methods and experimentation, often considered a precursor to the scientific method. He emphasized the importance of mathematics and observation, even predicting inventions like flying machines and submarines. Though his ideas were often met with resistance, they sowed seeds for future intellectual revolutions. The Renaissance marked a profound turning point, a rebirth of classical learning, and a renewed emphasis on human observation and reason. Artists like Leonardo da Vinci were also keen observers of the natural world, conducting detailed anatomical studies and designing ingenious machines, blurring the lines between art, engineering, and science. His notebooks are filled with observations on fluid dynamics, geology, and human anatomy, demonstrating a spirit of empirical inquiry that transcended disciplinary boundaries. The true revolution, however, began with the Copernican model of the solar system. Nicolaus Copernicus, a Polish astronomer, proposed a heliocentric model, placing the sun at the center of the universe, with the planets revolving around it. This was a radical departure from the long-held geocentric view and challenged both scientific and religious dogma. His work, De Revolutionibus Orbium Coelestium, published in 1543, ignited a slow but irreversible shift in cosmological understanding. It was a testament to the power of mathematical models to explain observed phenomena, even if those models contradicted common sense and established authority. Galileo Galilei, often called the father of observational astronomy and the father of modern physics, further solidified the heliocentric view. With his improved telescope, he made groundbreaking observations: the phases of Venus, which proved it orbited the Sun, the moons of Jupiter, demonstrating that not everything orbited Earth, and the mountains and craters on the Moon, showing that celestial bodies were not perfect, unblemished spheres, as Aristotle had taught. Galileo's experiments on motion, including his famous, though perhaps apocryphal, dropping of objects from the Leaning Tower of Pisa, challenged Aristotelian physics and laid the groundwork for Newton's laws of motion. His insistence on observation and experimentation, coupled with mathematical analysis, became a hallmark of the new scientific approach. The 17th century witnessed the formalization of the scientific method. Francis Bacon, an English philosopher, championed inductive reasoning, arguing that knowledge should be built upon systematic observation and experimentation, moving from specific instances to general principles. He advocated for a structured approach to inquiry, emphasizing the collection of data and the avoidance of preconceived notions. René Descartes, a French philosopher and mathematician, emphasized deductive reasoning, starting from self-evident truths and deriving conclusions through logical steps. His work in geometry, particularly the development of Cartesian coordinates, provided a powerful tool for describing physical space. The Royal Society of London, founded in 1660, became a crucial institution for promoting scientific inquiry. Its motto, Nullius in Verba, on the word of no one, underscored its commitment to empirical evidence and experimental verification over reliance on authority. This period saw the emergence of scientific journals, allowing for the dissemination of research and fostering a collaborative yet critical scientific community. The culmination of this early modern scientific revolution came with Isaac Newton. His Philosophiae Naturalis Principia Mathematica, published in 1687, presented a unified system of mechanics and gravitation that explained both terrestrial and celestial phenomena. Newton's laws of motion and his law of universal gravitation provided a mathematical framework that accurately described the movement of planets, the falling of apples, and the tides. His work demonstrated the incredible power of mathematics to describe the physical world and established a paradigm for scientific inquiry that would dominate for centuries. He showed that the universe operated according to predictable, discoverable laws, ushering in an era of unprecedented scientific confidence. The 18th century, the Age of Enlightenment, saw the application of scientific principles to society and philosophy. Thinkers like Voltaire and Rousseau advocated for reason and empirical evidence in all aspects of life. Carl Linnaeus developed a hierarchical system for classifying living organisms, laying the foundation for modern taxonomy. Antoine Lavoisier, through meticulous experiments on combustion, established the law of conservation of mass and helped to dismantle the phlogiston theory, revolutionizing chemistry. His precise measurements and quantitative approach transformed chemistry from an alchemical art into a rigorous science. The 19th century brought forth an explosion of scientific discovery across many fields. John Dalton proposed the atomic theory, suggesting that matter is composed of indivisible particles called atoms. Michael Faraday made fundamental discoveries in electromagnetism, demonstrating the connection between electricity and magnetism, which later paved the way for electric motors and generators. Charles Darwin, through his extensive observations during the voyage of the HMS Beagle, developed the theory of evolution by natural selection, profoundly changing our understanding of life's diversity and origins. His work on the origin of species, published in 1859, provided a powerful, evidence-based explanation for the development of life, challenging prevailing creationist views. Louis Pasteur's work on germ theory revolutionized medicine, demonstrating that microorganisms cause disease and leading to the development of vaccines and pasteurization. James Clerk Maxwell unified electricity, magnetism, and light into a single theoretical framework with his equations, predicting the existence of electromagnetic waves and laying the groundwork for radio communication. Dmitry Mendeleev organized the known chemical elements into the periodic table, revealing underlying patterns and predicting the existence of undiscovered elements. These breakthroughs were not isolated events, but built upon centuries of cumulative knowledge, each discovery opening new avenues of inquiry. As we move into the 20th century, the pace of discovery accelerated exponentially. The early years saw two revolutionary theories shape our understanding of the universe: Albert Einstein's theories of relativity and the development of quantum mechanics. Special relativity, proposed in 1905, showed that space and time are not absolute, but are relative to the observer's motion, and famously established the equivalence of mass and energy with E equals mc squared. General relativity, published in 1915, described gravity not as a force, but as a curvature of space-time caused by mass and energy, leading to a new understanding of cosmology and black holes. Quantum mechanics, developed by a host of physicists, including Max Planck, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, revealed the bizarre and counterintuitive nature of reality at the atomic and subatomic scales. It showed that energy exists in discrete packets called quanta, that particles can behave as both waves and particles, and that the act of observation itself can influence the outcome of an experiment. This realm of quantum phenomena challenged classical notions of determinism and locality, introducing concepts like superposition and entanglement. The discovery of the structure of DNA by James Watson and Francis Crick in 1953, building on the work of Rosalind Franklin and Maurice Wilkins, unveiled the molecular basis of heredity, initiating the field of molecular biology and leading to the biotechnology revolution. The space race, beginning in the mid-20th century, pushed the boundaries of engineering and physics, culminating in human landings on the moon and the deployment of powerful space telescopes, allowing us to peer further into the cosmos than ever before. The development of computers and information technology has profoundly transformed scientific research, enabling complex simulations, massive data analysis, and global collaboration. From climate modeling to drug discovery, computational power has become an indispensable tool. The Large Hadron Collider, a massive particle accelerator, allows physicists to probe the fundamental constituents of matter, searching for new particles and forces, recreating conditions that existed moments after the Big Bang. This journey through the history of scientific inquiry reveals a continuous thread, a persistent human desire to understand, to question, and to explain. From the meticulous observations of ancient astronomers to the complex experiments of modern particle physicists, the essence remains the same: a systematic approach to uncovering the truths of the natural world. Each generation builds upon the knowledge of those who came before, refining theories, developing new tools, and pushing the boundaries of what is known. The scientific method, with its emphasis on observation, hypothesis, experimentation, and peer review, has proven to be an incredibly powerful engine for progress, a self-correcting mechanism that continually refines our understanding. The story of science is not just a collection of facts or discoveries. It is a story of human ingenuity, perseverance, and the relentless pursuit of knowledge. It is a testament to the power of collective effort, spanning cultures and centuries to illuminate the mysteries of the universe. And as we trace these paths through time, we can appreciate the gradual unfolding of understanding, the slow, deliberate journey from speculation to evidence, from myth to measurement. The intricate tapestry of scientific knowledge, woven thread by thread over millennia, continues to expand, revealing ever more layers of complexity and beauty in the world around us. This quiet, steady progression of understanding, built brick by brick, observation by observation, experiment by experiment, continues even now. It is a testament to the enduring human spirit of inquiry, a gentle, persistent curiosity that seeks to illuminate the darkness of the unknown. And as we drift deeper into this historical landscape, we find ourselves at the precipice of a new understanding, ready to explore the very nature of light itself, the fundamental messenger that carries so much of the universe's story to our waiting minds. The fundamental messenger that carries so much of the universe's story to our waiting minds. Light, in its myriad forms, has always been a profound enigma, a source of both wonder and scientific pursuit. For millennia, its true nature remained shrouded in philosophical debate and rudimentary observation. Ancient Greek thinkers, for instance, grappled with its essence, proposing theories that ranged from emissions from the eye to particles emanating from the object itself. Euclid, in his work Optica, around 300 BCE, described light traveling in straight lines, a foundational concept that still underpins much of geometric optics. He observed reflections and refractions, noting how light behaves when it encounters different surfaces and media. His work laid the groundwork for understanding how we perceive the world, even if the underlying mechanism of light itself remained elusive. Hero of Alexandria, a brilliant engineer and mathematician of the 1st century CE, further explored these principles. He posited that light travels along the shortest path between 2 points, a concept known as the principle of least time, though it would take many centuries for this idea to be fully articulated and understood in the context of wave theory. These early insights, though limited by the technology and conceptual frameworks of their time, demonstrated an inherent human desire to quantify and explain the phenomena of the natural world. They represent the very nascent stirrings of scientific inquiry, where observation leads to hypothesis, even if the means to definitively test those hypotheses were not yet available. The classical world also saw the development of early optical instruments. The Romans, for example, were known to use glass spheres filled with water as magnifiers, a simple but effective application of refractive principles. Seneca the Younger, a Roman philosopher, noted in the 1st century CE how small, indistinct letters appeared larger and clearer when viewed through a globe of glass filled with water. This observation, though perhaps made casually, hints at the potential for tools to extend human perception, a recurring theme in the history of science. The practical applications of optics, from magnifying glasses to early forms of lenses, slowly began to emerge, driven by necessity and curiosity. However, a significant leap in understanding light came during the Islamic Golden Age. Scholars like Ibn al-Haytham, known in the West as Al-Hazan, revolutionized the study of optics in the 11th century. His monumental work, Kitab al-Manazir, or Book of Optics, was a systematic and empirical investigation into the nature of light and vision. Al-Hazan meticulously debunked the prevailing Greek emission theory, which suggested that light rays originated from the eye. Through careful experiments, he demonstrated that light originates from external sources and reflects off objects into the eye, a concept that forms the basis of modern understanding of vision. Al-Hazan's methodology was remarkably modern. He used darkrooms, or camera obscuras, to study the properties of light, observing how images were formed when light passed through a small aperture. He investigated reflection from mirrors of various shapes, flat, spherical, cylindrical, and meticulously studied refraction, attempting to quantify the angles of incidence and refraction. His work included detailed anatomical descriptions of the eye and explanations of how vision occurs, integrating physics, mathematics, and anatomy in a way that was unprecedented. He even discussed the psychological aspects of perception, recognizing that vision is not merely a passive reception of light, but an active interpretation by the brain. His contributions extended beyond mere observation. He emphasized the importance of experimentation and mathematical proof. Alhazen's Book of Optics was translated into Latin in the 12th century and profoundly influenced European thinkers for centuries, including Roger Bacon, Johannes Kepler, and Isaac Newton. It laid the foundation for the scientific method as applied to optics, transforming the study of light from philosophical speculation into an empirical science. The very act of systematically testing hypotheses, of building apparatus to isolate variables, and of recording results with precision, these were hallmarks of Alhazen's approach, echoing down the corridors of scientific history. As Europe emerged from the Middle Ages, the ideas of Alhazen began to take root and flourish. The invention of spectacles in Italy in the late 13th century marked a practical triumph of optical knowledge, dramatically improving the quality of life for those with presbyopia. While the exact inventor is debated, figures like Salvino d'Armate or Alessandro della Spina are often credited. This seemingly simple invention had profound societal implications, allowing scholars and artisans to continue their work into old age, thereby contributing to the intellectual and economic vitality of the era. The ability to correct vision through shaped lenses was a direct application of the principles of refraction, even if the theoretical understanding of light was still evolving. The Renaissance brought a renewed interest in observation and artistic representation, which further intertwined with the study of light. Artists like Leonardo da Vinci meticulously studied anatomy and perspective, implicitly engaging with the principles of light and shadow. His notebooks contain observations on the camera obscura and the nature of light, reflecting a broader cultural shift towards empirical investigation. The camera obscura, originally a tool for studying light, became a practical aid for artists in rendering perspective and capturing realistic scenes, demonstrating the interplay between scientific discovery and artistic expression. The 17th century proved to be a pivotal era for the understanding of light. It was a period of intense scientific ferment, marked by the invention of powerful new instruments and the emergence of competing theories. The telescope, invented around 1608, revolutionized astronomy, allowing Galileo Galilei to make groundbreaking observations of the cosmos. His discovery of the phases of Venus, the moons of Jupiter, and the mountains on the moon provided compelling evidence for the Copernican model of the solar system, challenging centuries of geocentric dogma. The microscope, developed around the same time, opened up an entirely new world of the very small, revealing microorganisms and the intricate structures of biological tissues. Both instruments, born from a deeper understanding of lenses and light, dramatically extended the range of human perception, revealing previously invisible realms. These new tools spurred further investigations into the nature of light itself. René Descartes, in his 1637 work Dioptric, proposed a corpuscular theory of light, suggesting that light was composed of tiny, rapidly moving particles. He attempted to explain reflection and refraction using mechanical analogies, likening light particles to balls bouncing off surfaces or moving through different media. While his specific explanations for refraction were later found to be incorrect, his emphasis on a mechanistic, particulate view of light was influential. Descartes also contributed significantly to geometric optics, providing a mathematical framework for understanding how light rays propagate and how lenses form images. However, a contrasting view was gaining traction: the wave theory of light. Christian Huygens, a Dutch polymath, was a prominent proponent of this idea. In his 1678 treatise, Traité de la Lumière, Treatise on Light, published in 1690, Huygens proposed that light consists of waves propagating through an ethereal medium, which he called the luminiferous aether. He developed the Huygens principle, which states that every point on a wavefront can be considered as a source of secondary spherical wavelets, and the new wavefront is the envelope of these wavelets. This principle elegantly explained reflection and refraction, including the phenomenon of double refraction observed in Iceland spar, a crystal that splits a single ray of light into two. Huygens' wave theory provided a more intuitive explanation for certain phenomena than Descartes' corpuscular theory. For instance, it could explain how light spreads out after passing through a small opening, a phenomenon known as diffraction, although a comprehensive explanation of diffraction would come later. The idea of light as a wave also resonated with observations of sound, which was known to be a wave phenomenon. The debate between the particle and wave theories of light would continue for centuries, becoming one of the most enduring scientific controversies. Amidst this debate, Isaac Newton, arguably the most influential scientist of his age, conducted his own groundbreaking experiments on light and color. In the 1660s, during his Annus Mirabilis, or Year of Wonders, while at home during the Great Plague, Newton famously used prisms to demonstrate that white light is not pure, but is composed of a spectrum of colors. He showed that when white light passes through a prism, it separates into its constituent colors: red, orange, yellow, green, blue, indigo, and violet, and that these colors cannot be further broken down. Crucially, he then used a second prism to recombine these colors back into white light, proving that the prism did not create the colors but merely separated them. This discovery, detailed in his 1672 paper to the Royal Society and later in his monumental work Optics, 1704, revolutionized the understanding of color. Before Newton, many believed that prisms somehow stained or modified white light. Newton's experiments demonstrated that color is an intrinsic property of light itself, with different colors corresponding to different degrees of refrangibility, or how much they bend when passing through a medium. He also developed a sophisticated corpuscular theory of light, arguing that light consisted of tiny particles, or corpuscles, traveling at immense speeds. He believed this theory could better explain the sharp shadows cast by objects and the rectilinear propagation of light. Newton's immense authority and the explanatory power of his corpuscular theory led it to dominate scientific thought for over a century, overshadowing Huygens' wave theory. His work on optics was not just theoretical. He also invented the reflecting telescope, which used mirrors instead of lenses to avoid chromatic aberration, the blurring of images caused by lenses refracting different colors of light at different angles. This invention was a significant practical advancement, paving the way for larger and more powerful telescopes. The 18th century, while building on Newton's foundations, saw fewer dramatic breakthroughs in the fundamental understanding of light. Instead, it was a period of consolidation and refinement of existing theories, particularly in geometric optics and the design of optical instruments. Mathematicians and instrument makers improved lens grinding techniques and developed achromatic lenses, which combined different types of glass to minimize chromatic aberration, allowing for clearer images in refracting telescopes and microscopes. Figures like John Dulland made significant contributions to the practical application of optical principles. However, the early 19th century witnessed a resurgence of the wave theory, driven by new experimental evidence that Newton's corpuscular theory struggled to explain. Thomas Young, an English polymath, conducted his famous double-slit experiment in 1801. By passing light through two closely spaced slits, he observed an interference pattern of bright and dark fringes on a screen behind them. This pattern, a characteristic of waves, could not be explained by particles traveling in straight lines. If light were particles, one would expect to see only two bright lines corresponding to the slits. Young's experiment provided compelling evidence for the wave nature of light, demonstrating that light waves could interfere with each other, much like water waves or sound waves. Young also proposed that different colors of light corresponded to different wavelengths, a concept that harmonized with Huygens' earlier ideas. His work was initially met with skepticism, largely due to the lingering influence of Newton's corpuscular theory. However, another brilliant scientist, Augustin Jean Fresnel, independently developed a comprehensive wave theory of light in the early 19th century. Fresnel, a French engineer and physicist, mathematically refined Huygens' principle and developed equations to describe diffraction, interference, and polarization. Fresnel's work provided a robust mathematical framework for the wave theory, explaining phenomena like the Poisson spot or Arago spot, a bright spot that appears in the center of the shadow of a circular opaque object when illuminated by a point source of light. This phenomenon, initially predicted by Poisson as a paradoxical consequence of Fresnel's wave theory, was experimentally confirmed by Arago, turning what was intended as a refutation into strong evidence for the wave nature of light. Fresnel's theory also explained polarization, the phenomenon where light waves oscillate in a specific plane, by proposing that light waves are transverse, meaning their oscillations are perpendicular to the direction of propagation. The triumph of the wave theory of light was largely complete by the mid-19th century. Yet, the question of the medium through which these light waves propagated remained. The luminiferous aether, a hypothetical omnipresent substance, was posited to fill all space, acting as the carrier for light waves. Its properties were extraordinary. It had to be rigid enough to support the high frequencies of light waves, yet tenuous enough to offer no resistance to the motion of planets. Scientists spent decades trying to detect this elusive aether, leading to the famous Michelson-Morley experiment of 1887. Albert Michelson and Edward Morley attempted to detect the aether wind that should have been created by the Earth's motion through the stationary aether. Using an interferometer, a device designed to measure tiny differences in the speed of light, they expected to see a shift in interference patterns as the Earth moved relative to the aether. To their surprise, and after repeated, meticulous experiments, they found no such shift. Their results were consistently null, suggesting that the speed of light was constant regardless of the Earth's motion. This unexpected outcome posed a profound challenge to the prevailing wave theory and the concept of the luminiferous aether. The Michelson-Morley experiment, though a failure in its original intent, became one of the most important null results in scientific history. It ultimately paved the way for Albert Einstein's special theory of relativity in 1905, which postulated that the speed of light in a vacuum is constant for all inertial observers, regardless of the motion of the light source or the observer. This revolutionary idea eliminated the need for the luminiferous aether entirely, fundamentally altering our understanding of space, time, and the universe. However, even as the wave nature of light seemed firmly established, new puzzles began to emerge at the turn of the 20th century, hinting that the story of light was far from complete. Experiments involving the interaction of light with matter, particularly the photoelectric effect, presented phenomena that the classical wave theory struggled to explain. The photoelectric effect, observed when light shines on a metal surface and causes electrons to be ejected, showed that the energy of the ejected electrons depended only on the frequency of the light, not its intensity. Below a certain threshold frequency, no electrons were emitted, regardless of how bright the light was. In 1900, Max Planck introduced the concept of energy quantization to explain black body radiation, proposing that energy is emitted and absorbed in discrete packets, or quanta. 5 years later, in 1905, Albert Einstein extended Planck's idea to light itself. He proposed that light consists of discrete packets of energy, which he called light quanta, or photons. Each photon's energy was directly proportional to its frequency, a relationship given by Planck's constant. This revolutionary idea, for which Einstein later received the Nobel Prize, elegantly explained the photoelectric effect. A single photon, if it had enough energy, i.e., high enough frequency, could knock an electron out of the metal, regardless of the number of other photons present. If the photon's energy was too low, no electron would be ejected. This reintroduction of a particle-like nature to light, after a century of dominance by the wave theory, was initially met with considerable resistance. It seemed to resurrect Newton's corpuscular theory, but in a much more sophisticated form. The scientific community grappled with the apparent contradiction. How could light be both a wave and a particle? This paradox led to the concept of wave-particle duality, a cornerstone of quantum mechanics. Light exhibits wave-like properties in phenomena like interference and diffraction, but particle-like properties in interactions with matter, such as the photoelectric effect. It behaves as a wave when propagating and as a particle when interacting. This duality is not a simple alternation between two states, but a fundamental aspect of reality at the quantum level. It suggests that our classical categories of wave and particle are insufficient to fully describe the true nature of light, and indeed, of all quantum entities. The quantum realm operates under rules that defy everyday intuition, where entities can exist in multiple states simultaneously, and where observation itself can influence the outcome of an experiment. The journey to understand light, from Euclid's straight lines to Einstein's photons, continues to inspire curiosity and awe, mirrors the broader evolution of scientific thought, a continuous process of observation, hypothesis, experimentation, and refinement. Each new discovery, each challenge to existing paradigms, has pushed the boundaries of human knowledge, revealing deeper layers of complexity and interconnectedness in the universe. The story of light is a testament to the persistent human drive to comprehend the fundamental forces that shape our reality. A gentle, persistent curiosity that seeks to illuminate the darkness of the unknown. And as we continue our exploration of science, we find ourselves on the threshold of even more profound discoveries, ready to delve into the intricate dance between energy and matter, the very fabric of existence itself. As the light of understanding continues its gentle diffusion, we find ourselves drawn into the very fabric of reality itself, the intricate dance of physics and chemistry. These two foundational sciences, often intertwined, seek to unravel the fundamental principles governing matter, energy, space, and time. Physics, in its broadest sense, is the study of these grand interactions, while chemistry focuses on matter and its properties, exploring how substances change and combine. Together, they paint a comprehensive picture of the universe, from the smallest subatomic particles to the vast expanse of galaxies. Our journey through these realms often begins with the most fundamental constants, those unchanging values that define the universe's behavior. The speed of light in a vacuum, for instance, is one such constant, an astonishing 299,792,458 meters per second. This cosmic speed limit is not merely a number, it is a cornerstone of our understanding of space and time, a central tenet of Albert Einstein's theory of relativity. This theory, a profound shift in scientific thought, revealed that space and time are not separate, immutable entities, but are interwoven into a single continuum, space-time, which can be warped by mass and energy. The faster an object moves, the more time slows down for it relative to a stationary observer, a concept that challenges our everyday perceptions. Gravity, another fundamental force, is the invisible sculptor of the cosmos. It is the force that attracts any two objects with mass, holding planets in orbit around stars, stars within galaxies, and galaxies within clusters. Isaac Newton first described its mathematical behavior, but it was Einstein who later provided a more complete picture, explaining gravity not as a force pulling objects together, but as the curvature of space-time caused by mass and energy. Imagine a bowling ball placed on a stretched rubber sheet. It creates a dip, and smaller marbles rolling nearby will be drawn towards the bowling ball, not by a direct pull, but by the distortion of the sheet itself. This analogy, though imperfect, offers a glimpse into the elegant complexity of general relativity. Beyond gravity, electromagnetism governs the interactions between electrically charged particles. This force is responsible for light, for electricity, for magnetism, and for holding atoms and molecules together. It is a unified force, meaning that electricity and magnetism are not separate phenomena, but two aspects of the same electromagnetic field. James Clerk Maxwell, in the 19th century, formulated a set of equations that beautifully described this unification, predicting the existence of electromagnetic waves traveling at the speed of light. His work laid the foundation for radio, television, and countless other technologies that shape our modern world. Thermodynamics is another essential branch of physics, concerned with heat and its relationship to other forms of energy and work. It introduces concepts like temperature, entropy, and the conservation of energy. The principle of conservation of energy states that energy cannot be created or destroyed, only transformed from one form to another. A light bulb, for example, transforms electrical energy into light and heat. A car engine converts chemical energy from fuel into kinetic energy to move the vehicle along with a significant amount of heat. These transformations are never perfectly efficient, and some energy is always lost to the environment as heat, increasing the overall disorder of the system. This concept of disorder brings us to entropy, a measure of randomness or unavailability of energy to do work in a closed system. The scientific concept of entropy dictates that in any isolated system, entropy tends to increase over time. This means that systems naturally move from order to disorder, from concentrated energy to dispersed energy. It is why a drop of ink spreads out in water, why a hot cup of coffee cools down, and why the universe, over vast timescales, is expected to become a state of maximum entropy, a uniform, cold, and dark expanse. This idea, while seemingly bleak, is a profound statement about the arrow of time itself. Delving deeper into the microscopic world, we encounter quantum mechanics, a revolutionary theory that describes the behavior of matter and energy at the atomic and subatomic levels. At these scales, the familiar rules of classical physics break down, and particles exhibit strange, counterintuitive behaviors. Energy, for instance, is not continuous, but comes in discrete packets called quanta. Max Planck introduced the Planck constant, a fundamental constant in quantum mechanics, illustrating this quantized nature of energy. It is an incredibly small number, but it underpins the entire quantum realm, revealing that energy is emitted or absorbed in tiny, indivisible units. One of the most famous principles of quantum mechanics is Heisenberg's uncertainty principle. It states that certain pairs of physical properties, such as a particle's position and momentum, cannot both be known with perfect precision simultaneously. The more accurately you measure one, the less accurately you can know the other. This is not a limitation of our measuring instruments. It is a fundamental property of nature itself. It suggests that at the quantum level, reality is not as fixed or deterministic as we perceive it to be in our macroscopic world. The Bohr model of the atom, though later superseded by more sophisticated quantum models, was a crucial step in understanding atomic structure. Niels Bohr proposed that electrons orbit the nucleus in specific energy levels or shells, and they can jump between these levels by absorbing or emitting discrete packets of energy. This model successfully explained the spectral lines of hydrogen, providing strong evidence for the quantized nature of atomic energy. While simplified, it laid the groundwork for the more complex quantum mechanical description of electron orbitals, which are not neat circles, but probability clouds where electrons are most likely to be found. The standard model of particle physics represents a pinnacle of scientific synthesis, describing the fundamental forces and particles that make up the universe. It categorizes all known elementary particles, including quarks, leptons, and bosons, and explains how they interact through the strong, weak, and electromagnetic forces. It is an incredibly successful theory, having predicted the existence of many particles that were later experimentally confirmed. One of the most significant confirmations was the discovery of the Higgs boson, sometimes called the God particle. The Higgs boson is an elementary particle associated with the Higgs field, which permeates all of space and gives other fundamental particles their mass. Its experimental confirmation at the Large Hadron Collider in 2012 was a monumental achievement, providing crucial insight into the origin of mass itself. Another mind-bending concept from quantum science is quantum entanglement. This phenomenon describes how two particles can become linked in such a way that they share the same fate, instantly affecting each other regardless of the distance separating them. If you measure a property of one entangled particle, you instantaneously know the corresponding property of the other, even if they are light years apart. Einstein famously called this spooky action at a distance, as it seems to violate our classical understanding of locality. However, numerous experiments have confirmed its reality, opening up possibilities for quantum computing and quantum communication. Chemistry, the sister science to physics, builds upon these fundamental principles to explore the composition, structure, properties, and reactions of matter. The periodic table, a masterpiece of chemical organization, arranges all known chemical elements by atomic number, electron configuration, and recurring chemical properties. Dmitry Mendeleev, in the 19th century, developed one of the earliest versions, famously leaving gaps for elements yet to be discovered, accurately predicting their properties. Today, it is an indispensable tool for chemists, revealing patterns and relationships between elements that govern their behavior. The pH scale is another essential concept in chemistry, measuring the acidity or alkalinity of a solution. It ranges from 0 to 14, with 7 being neutral. Solutions with a pH below 7 are acidic, meaning they have a higher concentration of hydrogen ions, while solutions with a pH above 7 are alkaline or basic, indicating a higher concentration of hydroxide ions. This simple scale has profound implications, influencing everything from biological processes in our bodies to industrial chemical reactions and environmental science. Absolute zero, the lowest possible temperature, is a concept shared by both physics and chemistry. It is defined as negative 273.15 degrees Celsius, or 0 Kelvin. At this temperature, all atomic and molecular motion theoretically ceases, and a system possesses its minimum possible energy. While absolute zero can never be perfectly reached in practice, scientists have achieved temperatures incredibly close to it in laboratories, revealing exotic quantum phenomena like superconductivity and superfluidity. From the elegant symmetries of physics and the intricate transformations of chemistry, we now shift our gaze to the vibrant tapestry of the living world. Biology, the study of life itself, explores organisms in all their bewildering diversity, from their microscopic structures to their grand evolutionary histories. It seeks to understand how life functions, grows, evolves, and interacts with its environment. Geology, on the other hand, delves into the Earth's physical structure, its vast history, and the dynamic processes that shape its surface and interior. It is the story of mountains rising and falling, oceans forming and receding, and continents drifting across the globe over millions of years. Ecology bridges these two realms, focusing on the intricate relationships between living organisms and their environment. It examines how species interact with each other, how populations grow and decline, and how ecosystems maintain their delicate balance. The concept of the edge effect in ecology, for instance, describes changes in population or community structures that occur at the boundary of two or more habitats. These transitional zones, or ecotones, often exhibit higher biodiversity than the adjacent habitats, as species from both areas can thrive there. The theory of evolution by natural selection, proposed independently by Charles Darwin and Alfred Russel Wallace, stands as a cornerstone of modern biology. It explains the diversity of life on Earth, proposing that species change over time through a process where individuals with traits best suited to their environment are more likely to survive and reproduce, passing those advantageous traits to their offspring. This gradual accumulation of favorable traits leads to the formation of new species and the incredible adaptation we observe in the natural world. At the heart of all life lies DNA, or deoxyribonucleic acid. This remarkable molecule carries the genetic instructions used in the growth, development, functioning, and reproduction of all known living organisms. The discovery of the structure of DNA by James Watson and Francis Crick, building on the crucial X-ray diffraction work of Rosalind Franklin and Maurice Wilkins, unlocked the secrets of heredity and laid the foundation for molecular biology. It revealed the elegant double helix, a ladder-like structure where two strands are twisted around each other, with specific base pairs forming the rungs. This structure immediately suggested how genetic information could be copied and passed down through generations. The study of genetics, which began with Gregor Mendel's meticulous experiments on pea plants in the mid-19th century, has progressed exponentially. Mendel's work on inheritance patterns, though initially overlooked, laid the groundwork for understanding how traits are passed from parents to offspring. From his simple observations of pea plant characteristics, we have now reached the era of CRISPR gene editing technology. CRISPR-Cas9 allows scientists to make precise modifications to DNA, effectively cutting and pasting genetic material with unprecedented accuracy. This revolutionary tool holds immense promise for treating genetic diseases, developing new crops, and advancing our understanding of gene function. The Human Genome Project, a monumental scientific endeavor, successfully mapped the entire human genetic code. Completed in 2003, this project provided a complete sequence of the approximately 3 billion DNA base pairs that make up the human genome. It revolutionized biology and medicine, offering an unprecedented blueprint for understanding human health and disease. This vast trove of information continues to be explored, revealing insights into human evolution, individual differences, and the genetic basis of complex traits. Within our own bodies, a bustling ecosystem thrives, the microbiome. This is the collection of all microbes, including bacteria, fungi, and viruses, living in and on the human body. Far from being mere passengers, these microscopic inhabitants play crucial roles in digestion, immune system development, and even mental health. The study of the microbiome is a rapidly expanding area of scientific research, revealing its profound influence on human well-being. The human brain itself is an astonishing marvel of biological engineering, containing approximately 86 billion neurons. These specialized cells communicate through electrical and chemical signals, forming complex networks that give rise to thought, emotion, memory, and consciousness. Neuroscience, the scientific study of the nervous system, seeks to unravel the mysteries of this most complex organ, exploring everything from the molecular mechanisms of synaptic transmission to the neural correlates of subjective experience. On a larger scale, the Earth itself is a dynamic, living system. The theory of plate tectonics revolutionized geology by explaining continental drift, earthquakes, and volcanic activity. It posits that the Earth's lithosphere, its rigid outer shell, is broken into large plates that are constantly moving, driven by convection currents in the underlying mantle. Where these plates collide, pull apart, or slide past each other, we see the dramatic geological phenomena that shape our planet's surface. The Earth's magnetic field, generated by the motion of molten iron in its outer core, acts as a protective shield. It deflects harmful charged particles from the solar wind and cosmic rays, safeguarding life on the surface. Without this invisible force field, our atmosphere would likely have been stripped away by the sun's radiation, making the planet uninhabitable. Seismology, the scientific study of earthquakes and seismic waves, allows us to probe the Earth's interior and understand these powerful geological events. The ozone layer, a region in Earth's stratosphere, plays a vital role in protecting life by absorbing most of the sun's harmful ultraviolet radiation. This natural shield is crucial for preventing skin cancer, cataracts, and damage to plant life. The discovery of the depletion of the ozone layer due to human-made chemicals and the subsequent global effort to address it stands as a testament to the power of scientific understanding and international cooperation. Photosynthesis, the process used by plants, algae, and cyanobacteria, is the fundamental engine of most life on Earth. These organisms convert light energy into chemical energy, primarily in the form of glucose, using carbon dioxide and water. This process releases oxygen as a byproduct, replenishing the atmosphere and providing the air we breathe. Without photosynthesis, the vast majority of food chains would collapse, and the Earth's atmosphere would be dramatically different. The study of climate change involves multiple scientific disciplines, including atmospheric science, oceanography, and glaciology. It examines how the Earth's climate system is changing, primarily due to human activities, and the potential impacts of these changes. The greenhouse effect is a natural scientific phenomenon where certain gases in Earth's atmosphere, such as carbon dioxide and methane, trap heat, keeping the planet warm enough to support life. However, an enhanced greenhouse effect, caused by increased concentrations of these gases from human emissions, is leading to global warming and disruptions to climate patterns. As we consider the intricate dance of physics and chemistry, the vibrant complexity of biology, and the dynamic processes of Earth sciences, we begin to appreciate the profound interconnectedness of all scientific inquiry. Each discovery, each theory, each constant builds upon the last, deepening our understanding of the universe and our place within it. These explorations, from the subatomic to the planetary, reveal a cosmos of exquisite order and constant transformation. The pursuit of this knowledge is a gentle, persistent unraveling of the world's secrets, inviting us to witness the quiet majesty of existence. This quiet majesty of existence, revealed through the lens of scientific exploration, extends its gaze from the grand cosmic ballet to the intricate dance of life itself. We have journeyed through the foundational principles of physics and chemistry, touched upon the vastness of space, and considered the dynamic processes shaping our planet. Now our focus gently shifts, drawing closer to the vibrant, complex tapestry of biology. Biology, in its broadest sense, is the study of living organisms and their vital processes. It encompasses a breathtaking array of scales, from the molecular machinery within a single cell to the global interactions of entire ecosystems. This field seeks to understand how life originates, evolves, functions, and interacts. Its history is a story of meticulous observation, groundbreaking experimentation, and profound conceptual shifts. Early biological thought, often intertwined with medicine and philosophy, dates back to ancient civilizations. Figures like Aristotle in ancient Greece undertook systematic observations of animals, classifying them based on their characteristics and behaviors. His work, though lacking modern experimental methods, laid some groundwork for comparative anatomy and zoology. In the Roman Empire, Galen's anatomical studies, primarily on animals, provided insights into the human body that would influence medical understanding for over a millennium. The Renaissance brought a renewed spirit of inquiry. Andreas Vesalius, in the 16th century, revolutionized anatomy with his detailed dissections of human cadavers, correcting many of Galen's long-held errors. His magnificent anatomical atlases, like De Humani Corporis Fabrica, were masterpieces of both scientific illustration and empirical investigation. This period also saw the emergence of botany as a distinct discipline, with naturalists meticulously cataloging and describing plants, often for their medicinal properties. The invention of the microscope in the 17th century marked a pivotal moment. Antony van Leeuwenhoek, a Dutch draper, ground his own lenses with remarkable skill, achieving magnifications far beyond his contemporaries. Through his simple single-lens microscopes, he became the first to observe bacteria, protozoa, sperm cells, and blood cells. He called these tiny living things animalcules, opening up an entirely new, unseen world of microscopic life. Robert Hooke, an English polymath, also used a compound microscope to examine cork, coining the term cell to describe the tiny box-like compartments he observed, a term that would become fundamental to all biology. The 18th century saw Carolus Linnaeus develop his system of binomial nomenclature, a standardized way of naming species using two Latinized terms, genus and species. This system, still in use today, brought order to the chaotic diversity of life, allowing scientists across the globe to communicate precisely about specific organisms. His work, Systema Naturae, was a monumental effort to classify all known plants and animals, providing a framework for understanding their relationships. The 19th century witnessed an explosion of biological discoveries and theoretical advancements. Jean-Baptiste Lamarck proposed a theory of evolution based on the inheritance of acquired characteristics, suggesting that traits developed during an organism's lifetime could be passed to its offspring. While ultimately disproven in its specific mechanism, Lamarck's ideas were important in challenging the prevailing view of species as immutable. The most transformative idea of the 19th century came from Charles Darwin and Alfred Russel Wallace, who independently conceived of evolution by natural selection. Darwin's monumental work on the origin of species, published in 1859, meticulously presented evidence for descent with modification, arguing that all life shares a common ancestor, and that species change over time through a process where individuals with advantageous traits are more likely to survive and reproduce. This theory provided a powerful, unifying explanation for the diversity of life, its adaptations, and its distribution across the planet. Around the same time, Gregor Mendel, an Augustinian friar, conducted meticulous experiments with pea plants in his monastery garden. His work, published in 1866, but largely unrecognized for decades, uncovered the fundamental laws of heredity. Mendel demonstrated that traits are passed from parents to offspring in discrete units, which he called factors, what we now know as genes. His principles of segregation and independent assortment laid the foundation for the science of genetics. The early 20th century saw the rediscovery of Mendel's work and its integration with Darwinian evolution, leading to the modern synthesis. This synthesis reconciled genetics with natural selection, providing a robust framework for understanding how evolutionary change occurs at the genetic level. Scientists like Thomas Hunt Morgan, working with fruit flies, provided crucial experimental evidence for Mendelian inheritance and the chromosomal theory of heredity, showing that genes are located on chromosomes. Biochemistry, the study of the chemical processes within living organisms, also blossomed in the 20th century. The understanding of enzymes as biological catalysts, the elucidation of metabolic pathways like glycolysis and the Krebs cycle, and the identification of vitamins as essential organic compounds were all crucial developments. These discoveries began to bridge the gap between the macroscopic world of organisms and the microscopic world of molecules. The mid-20th century brought perhaps the most profound biological discovery of all: the structure of DNA. In 1953, James Watson and Francis Crick, building on the X-ray diffraction work of Rosalind Franklin and Maurice Wilkins, proposed the double helix model for deoxyribonucleic acid. This elegant structure immediately suggested how genetic information could be stored, replicated, and passed down through generations. The discovery of DNA's structure opened the floodgates for molecular biology, transforming our understanding of life at its most fundamental level. Following the DNA discovery, the genetic code, how the sequence of bases in DNA is translated into the sequence of amino acids and proteins, was deciphered. Scientists like Marshall Nierenberg and Har Gobind Khorana played key roles in this monumental effort. This understanding revealed the universal language of life, demonstrating that the same genetic code is used by nearly all organisms on Earth, from bacteria to humans, a powerful testament to common ancestry. The development of recombinant DNA technology in the 1970s, pioneered by scientists like Paul Berg, Herbert Boyer, and Stanley Cohen, allowed for the manipulation of genes. This revolutionary technology made it possible to cut and paste DNA segments, transfer genes between organisms, and produce specific proteins in large quantities. This ushered in the era of biotechnology, with applications ranging from medicine to agriculture. The late 20th and early 21st centuries have been dominated by genomics, the study of entire genomes. The Human Genome Project, an ambitious international effort completed in 2003, sequenced the entire human genome, providing a complete blueprint of our genetic makeup. This project and subsequent genomic studies have revealed the complexity of gene regulation, the vastness of non-coding DNA, and the genetic basis of many diseases. Beyond the molecular and genetic realms, biology continues to explore the intricate workings of organisms. Physiology investigates how living systems function, from the pumping of the heart to the firing of neurons. Neuroscience, a rapidly expanding field, delves into the complexities of the brain and nervous system, seeking to understand consciousness, memory, and perception. Immunology studies the body's defense mechanisms against disease, while developmental biology examines how a single fertilized egg develops into a complex multicellular organism. Ecology, another vital branch of biology, studies the interactions between organisms and their environment. It explores how populations grow and decline, how communities are structured, and how ecosystems function, including the flow of energy and the cycling of nutrients. Understanding ecological principles is crucial for addressing pressing global challenges such as climate change, biodiversity loss, and resource management. Conservation biology, an applied field, uses ecological principles to protect and restore biodiversity. The study of evolution continues to be a central unifying theme in biology. Evolutionary developmental biology, or EVER-DEVO, compares the developmental processes of different organisms to infer their ancestral relationships and understand how developmental changes can lead to new forms. Paleontology, the study of fossils, provides direct evidence of past life and the history of evolution on Earth. Biology is not a static field. It is constantly evolving, driven by new technologies and innovative approaches. High-throughput sequencing technologies allow for rapid and cost-effective sequencing of entire genomes, leading to personalized medicine and a deeper understanding of microbial communities. Advanced microscopy techniques provide unprecedented views into the inner workings of cells and tissues. Computational biology and bioinformatics are essential for managing and analyzing the vast amounts of data generated by modern biological research. The interconnectedness of biological systems is a recurring theme. From the intricate feedback loops within a cell to the complex food webs in an ecosystem, life is characterized by dynamic interactions. The concept of homeostasis, the ability of an organism to maintain stable internal conditions despite external changes, highlights the delicate balance required for life to persist. Consider the human body, a marvel of biological engineering. Trillions of cells, each a miniature factory, work in concert. Neurons transmit electrical signals at incredible speeds, forming thoughts and memories. Muscle cells contract, enabling movement. Immune cells patrol for invaders, defending against disease. Hormones regulate growth, metabolism, and reproduction. All these processes are orchestrated with astonishing precision, a testament to billions of years of evolutionary refinement. The diversity of life on Earth is astounding. From the extremophiles thriving in boiling hot springs or deep-sea vents, to the towering redwood trees and the microscopic plankton that form the base of marine food webs, life has adapted to almost every conceivable niche. This biodiversity is not just a wonder to behold, it is essential for the health and stability of our planet's ecosystems. Each species, no matter how small, plays a role in the intricate web of life. With its emphasis on observation, hypothesis testing, experimentation, and peer review, is the bedrock of biological discovery. Biologists formulate questions, design experiments to test their hypotheses, collect and analyze data, and draw conclusions that are subject to scrutiny by the broader scientific community. This rigorous process ensures the reliability and validity of biological knowledge. The pursuit of biological understanding is driven by both curiosity and practical necessity. Basic research, aimed at understanding fundamental biological processes, often lays the groundwork for applied research that leads to new treatments for diseases, improved agricultural practices, or novel biotechnologies. For instance, the discovery of CRISPR-Cas9, a bacterial immune system, has been repurposed into a revolutionary gene editing tool with immense potential for medicine and agriculture. As we delve deeper into the biological sciences, we find ourselves contemplating the very essence of what it means to be alive. The boundaries between living and non-living matter, once thought to be distinct, become blurred at the molecular level, where complex organic molecules self-assemble and replicate. The origin of life itself remains one of biology's most profound unanswered questions, a frontier of ongoing research. The journey through biology is a journey into ourselves and into the living world that surrounds us. It reveals the shared heritage of all organisms, the elegant mechanisms that sustain life, and the dynamic processes that drive evolution. It teaches us about resilience, adaptation, and the delicate balance of nature. This exploration, like a gentle current, carries us further into the quiet depths of understanding, inviting a peaceful contemplation of life's intricate dance. The silent hum of cellular machinery, the slow unfolding of evolutionary time, the quiet growth of a forest, all these biological wonders contribute to the profound stillness that science unveils. This stillness extends beyond the living world, reaching into the very fabric of the cosmos, where the grand narratives of physics and astronomy unfold with a similar, majestic slowness. We turn our gaze now to the vastness beyond Earth, to the celestial mechanics that govern planets and stars, and to the fundamental forces that shape the universe itself. Consider the gentle pull of gravity, an invisible force that orchestrates the dance of cosmic bodies. It is gravity that holds galaxies together, binding billions of stars into magnificent spirals and ellipses. It is gravity that sculpts planetary systems, guiding rocky worlds and gas giants in their endless orbits around central suns. This fundamental interaction, described by Isaac Newton in the 17th century, revolutionized our understanding of the heavens. Newton's law of universal gravitation stated that every particle of matter attracts every other particle with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This elegant mathematical formulation explained the falling of an apple and the orbital paths of the moon and planets with equal precision. Before Newton, celestial motions were often described by complex geometric models, like Ptolemy's geocentric system, with its intricate epicycles and deferents. Newton's work unified terrestrial and celestial mechanics, demonstrating that the same laws applied everywhere. His Principia Mathematica, published in 1687, laid the foundation for classical mechanics and provided a framework for understanding the universe as a predictable, clockwork mechanism. The implications were profound, suggesting a universe governed by immutable laws, discoverable through observation and reason. Centuries later, Albert Einstein offered a new perspective on gravity with his theory of general relativity. Instead of a force acting at a distance, Einstein proposed that gravity is a manifestation of the curvature of space-time caused by mass and energy. Imagine a stretched rubber sheet and then place a heavy bowling ball on it. The ball creates a dip, and if you roll a marble nearby, it will curve towards the bowling ball, not because the bowling ball pulls it, but because the marble is following the curve in the sheet. Similarly, planets orbit the sun not because the sun exerts a direct force, but because the sun's immense mass warps the space-time around it, and the planets follow these curves. This concept, though abstract, has been rigorously tested and confirmed through various observations, such as the bending of starlight around the sun during a solar eclipse, the gravitational redshift of light, and the precise orbital decay of binary pulsars. General relativity also predicted the existence of gravitational waves, ripples in space-time caused by accelerating massive objects, which were directly detected in 2015 by the LIGO experiment. These waves, traveling at the speed of light, offer a new way to observe the most energetic events in the universe, like the merging of black holes and neutron stars. The universe, in its vastness, is a testament to these fundamental forces. Stars, the radiant beacons of the cosmos, are born from collapsing clouds of gas and dust, primarily hydrogen and helium, under the relentless grip of gravity. As these clouds contract, the pressure and temperature at their core increase dramatically. When the temperature reaches millions of degrees Celsius, nuclear fusion ignites, converting hydrogen into helium and releasing enormous amounts of energy. This outward pressure from fusion balances the inward pull of gravity, creating a stable star, like our own sun, that can shine for billions of years. The life cycle of a star is a grand cosmic drama. Smaller stars, like the sun, will eventually swell into red giants, shedding their outer layers to form beautiful planetary nebulae, and leaving behind a dense, hot core called a white dwarf. These white dwarfs slowly cool over eons, becoming black dwarfs. More massive stars, however, meet a more spectacular end. After exhausting their nuclear fuel, their cores collapse under gravity, leading to a catastrophic supernova explosion that briefly outshines entire galaxies. These explosions scatter heavy elements, the building blocks of planets and life, across the cosmos. What remains after a supernova depends on the star's initial mass, either a super-dense neutron star, or if the star was massive enough, a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. The elements forged in the hearts of stars and scattered by supernova are the very atoms that constitute our bodies, our planet, and everything we see around us. Hydrogen and helium were created in the Big Bang, the universe's fiery beginning. But carbon, oxygen, iron, and all the other heavier elements were synthesized in stars. We are, quite literally, stardust. This profound connection between the microscopic and the macroscopic, between the fleeting existence of a human and the eternal cycle of stellar birth and death, offers a deep sense of belonging within the cosmic tapestry. Our solar system itself is a product of this stellar recycling. Approximately 4.6 billion years ago, a vast cloud of gas and dust, enriched by the remnants of previous generations of stars, began to collapse under its own gravity. As it contracted, it spun faster, flattening into a rotating disk. At the center, the material became so dense and hot that a protostar formed, eventually igniting to become our sun. In the cooler outer regions of the disk, dust grains collided and stuck together, gradually accreting into larger and larger bodies, forming planetesimals. These planetesimals continue to collide and merge, eventually forming the planets, moons, and other celestial bodies we observe today. The inner planets, Mercury, Venus, Earth, and Mars, are rocky terrestrial worlds, denser and smaller, having formed in the hotter parts of the disk where only silicates and metals could condense. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are gas giants, massive worlds composed primarily of hydrogen and helium, which accumulated in the colder outer regions where volatile compounds like water, methane, and ammonia could freeze and contribute to their growth. Each planet, with its unique characteristics, tells a story of its formation and evolution within this dynamic environment. Earth, our home, is a marvel of geological and biological processes. Its active geology, driven by plate tectonics, constantly reshapes its surface. The Earth's crust is broken into several large plates that slowly move, driven by convection currents in the underlying mantle. This movement causes earthquakes, volcanic eruptions, and the formation of mountain ranges. The continuous recycling of crustal material through subduction and uplift has played a crucial role in regulating Earth's climate and providing the necessary conditions for life to flourish. The Earth's atmosphere, a thin protective veil, is another critical component. Originally composed of gases released from volcanic activity, it has been profoundly altered by life itself. Early photosynthetic organisms, like cyanobacteria, began producing oxygen billions of years ago, gradually transforming the atmosphere into the oxygen-rich environment we breathe today. This great oxidation event was a pivotal moment in Earth's history, paving the way for the evolution of complex oxygen-dependent life forms. The study of Earth's climate, a complex system of interacting components, atmosphere, oceans, land surface, ice, and biosphere, reveals the delicate balance that sustains life. Climate science investigates long-term weather patterns, the factors that influence them, and how they have changed throughout geological time. It uses sophisticated models and extensive data from satellites, ground stations, and paleoclimate records, like ice cores and tree rings, to understand past climates and predict future trends. The interconnectedness of these systems means that changes in one component can have far-reaching effects on others, underscoring the intricate dance of Earth's natural processes. Beyond our solar system, the exploration of exoplanets, planets orbiting other stars, has become a vibrant field of astronomical research. Telescopes like Kepler and TESS have discovered thousands of these distant worlds, revealing a stunning diversity of planetary systems. Some exoplanets are gas giants, orbiting very close to their stars, known as hot Jupiters. Others are super-Earths, rocky planets larger than Earth, but smaller than Neptune. The search for exoplanets within the habitable zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface, is a key focus, as liquid water is considered essential for life as we know it. The methods used to detect exoplanets are ingenious. The transit method observes the slight dimming of a star's light as a planet passes in front of it. The radial velocity method detects the tiny wobble in a star's motion caused by the gravitational tug of an orbiting planet. Direct imaging, though more challenging, allows astronomers to capture actual photographs of exoplanets, especially large ones far from their stars. Each new discovery expands our understanding of planetary formation and the prevalence of planets in the galaxy, hinting at the possibility of life beyond Earth. The universe is not static. It is constantly expanding, a discovery made by Edwin Hubble in the early 20th century. By observing the redshift of light from distant galaxies, a phenomenon where light waves are stretched as the source moves away, similar to how the pitch of a siren lowers as it recedes, Hubble determined that almost all galaxies are moving away from us, and the farther away they are, the faster they recede. This observation led to the Big Bang Theory, the prevailing cosmological model describing the universe's origin and evolution. The Big Bang Theory posits that the universe began from an extremely hot, dense state approximately 13.8 billion years ago, and has been expanding and cooling ever since. Evidence supporting this theory includes the cosmic microwave background radiation, a faint glow of uniform radiation permeating the universe, which is interpreted as the afterglow of the Big Bang. The observed abundance of light elements, hydrogen, helium, and lithium, also matches the predictions of Big Bang nucleosynthesis, the process by which these elements were formed in the early universe. Cosmology, the study of the origin, evolution, and large-scale structure of the universe, delves into profound questions about existence itself. It explores concepts like dark matter and dark energy, mysterious components that make up about 95% of the universe's mass and energy content. Dark matter, which does not emit or absorb light, is inferred from its gravitational effects on visible matter, such as the rotation curves of galaxies and the gravitational lensing of distant objects. Dark energy, an even more enigmatic force, is thought to be responsible for the accelerating expansion of the universe. Its nature remains one of the greatest unsolved mysteries in physics. The scientific endeavor, in its relentless pursuit of knowledge, continually pushes the boundaries of human understanding. From the subatomic particles that constitute matter to the colossal structures of galaxy clusters, science seeks to unravel the fundamental laws that govern reality. It is a journey of discovery characterized by observation, experimentation, hypothesis formulation, and rigorous testing. Each new insight, each confirmed theory, adds another piece to the intricate puzzle of the cosmos. This journey is not just about facts and figures, it is about a way of thinking, a method for understanding the world. It emphasizes skepticism, critical thinking, and the willingness to revise one's understanding in the face of new evidence. Science is a collective human enterprise, built upon the work of countless individuals across generations and cultures, each contributing to the ever-growing edifice of knowledge. The quiet contemplation of these grand scientific narratives offers a profound perspective, a sense of humility in the face of the universe's immensity, and an appreciation for the intricate beauty of its underlying order. The gentle rhythm of scientific discovery, the slow unfolding of cosmic events, and the patient accumulation of understanding. These elements combine to create a tranquil landscape for the mind. We have journeyed from the microscopic wonders of biology to the vast scales of cosmology, each step revealing a deeper layer of complexity and elegance. The universe, in its silent operation, continues its grand, unhurried dance, inviting us to observe, to learn, and to find peace in its enduring mysteries. The profound stillness that science unveils is a constant, gentle presence, like the soft glow of distant starlight, guiding us deeper into the quietude of understanding. The gentle current of scientific inquiry continues its flow, carrying us further into the understanding of our world. We have seen how applied science translates fundamental discoveries into tangible benefits for humanity. Vaccination, for instance, stands as a monumental achievement, a scientific method designed to stimulate the immune system, providing protection against infectious diseases. It reshaped global health, dramatically reducing the incidence of many once devastating illnesses. The serendipitous discovery of penicillin by Alexander Fleming further revolutionized medicine. This accidental finding provided an effective treatment for bacterial infections, transforming the landscape of healthcare and saving countless lives. These breakthroughs highlight the profound impact of scientific innovation on daily existence. Beyond medicine, the realm of artificial intelligence, a branch of computer science, seeks to create intelligent machines. This field explores how computers can learn, reason, and solve problems, pushing the boundaries of what technology can achieve. Biotechnology, another transformative area, involves using living systems and organisms to develop products, ranging from new medicines to sustainable fuels. The discovery of X-rays by Wilhelm Röntgen, for example, revolutionized medical imaging. This invisible form of radiation allowed physicians to see inside the human body without invasive procedures, leading to more accurate diagnoses and treatments. Nanotechnology, the manipulation of matter on an atomic, molecular, and supramolecular scale, promises further advancements, enabling the creation of materials and devices with unprecedented properties. Scientific methods also provide tools for understanding the past. Radiocarbon dating, a precise technique, determines the age of organic materials by measuring the decay of carbon-14 isotopes. This method has been invaluable in archaeology, geology, and paleontology, offering insights into ancient civilizations and the history of life on Earth. Microscopy, the science of investigating small objects and structures, continually expands our visual perception. From early optical microscopes to powerful electron microscopes, these instruments reveal the intricate details of cells, microorganisms, and materials, unveiling hidden worlds. Even extreme conditions are subject to scientific investigation. Cryogenics, the study of the production and behavior of materials at very low temperatures, explores phenomena that occur near absolute zero. Such research has applications in fields like superconductivity and space exploration. The Doppler effect, a fundamental principle in physics, describes the change in frequency or wavelength of a wave in relation to an observer moving relative to the wave source. This effect is not only crucial in astronomy, helping us understand the movement of stars and galaxies, but also in medical imaging, such as ultrasound, providing vital diagnostic information. Applied science, in essence, focuses on using existing scientific knowledge to develop practical applications. This includes the creation of new technologies, the development of life-saving medicines, and the engineering of solutions to complex problems. Computational science, meanwhile, employs advanced computing to simulate processes that are too difficult or expensive to observe directly, offering powerful insights into complex systems, from climate models to protein folding. The scientific notation system, a practical tool, allows scientists to easily work with very large or very small numbers. It simplifies complex calculations and facilitates clear communication of vast quantities, like the distances between galaxies or the size of atoms. As we reflect on these tangible impacts, the journey naturally turns to the deeper philosophical underpinnings of science. The very way knowledge grows and evolves is a subject of profound inquiry. Thomas Kuhn introduced the concept of a scientific paradigm, describing distinct conceptual patterns or theories that shape a scientific discipline. These paradigms define what is studied, what questions are asked, and what constitutes a valid answer. Chaos theory, a field within mathematics and physics, deals with complex systems whose behavior is highly sensitive to slight changes in initial conditions. This butterfly effect illustrates how small perturbations can lead to vastly different outcomes, challenging long-term prediction in systems like weather or ecological models. Kuhn also described paradigm shifts, fundamental changes in the basic concepts and experimental practices of a scientific discipline. These shifts represent revolutions in thought, where old frameworks are replaced by new ones that offer more comprehensive explanations. Scientific consensus does not signify absolute certainty, but rather a collective judgment of a community of scientists based on available evidence. It is a dynamic state, subject to revision as new evidence emerges and understanding deepens. The reproducibility crisis, observed in some scientific fields, highlights the importance of independent verification of experimental results. The ability to replicate findings is a cornerstone of scientific rigor, ensuring the reliability and validity of research. Thought experiments, like Schrödinger's cat, are valid scientific tools. They explore the implications of theories without physical experimentation, pushing the boundaries of conceptual understanding. The null hypothesis is a foundational concept in scientific testing. It proposes no relationship between observed phenomena, and researchers then attempt to disprove it, seeking evidence for a significant effect. Serendipity, or accidental discovery, has played a significant role in numerous scientific breakthroughs. From penicillin to the cosmic microwave background radiation, chance encounters have often led to profound insights. The demarcation problem in the philosophy of science seeks to distinguish science from non-science, including pseudoscience. It explores the criteria that define scientific inquiry, such as empirical evidence, testability, and falsifiability. Peer review is a critical self-regulating process in science. Experts evaluate the quality and validity of research before publication, ensuring that findings meet rigorous standards. Metascience, a field that studies science itself, aims to improve its quality and efficiency. It examines research practices, publication processes, and the overall scientific enterprise to enhance its effectiveness. The observer effect in science refers to the phenomenon where the act of observing or measuring a phenomenon inevitably influences that phenomenon, where the act of measurement can alter the state of a particle. Occam's razor, while not a strict scientific law, is a guiding principle. It suggests that among competing hypotheses, the one with the fewest assumptions should be preferred, promoting simplicity and elegance in explanation. Citizen science projects involve public participation in scientific research. Individuals contribute to data collection and analysis across various disciplines, expanding the reach and scope of scientific inquiry. Epistemology, the study of knowledge, is deeply intertwined with science. It explores how scientific knowledge is acquired, justified, and validated, examining the very nature of what we consider to be true. The concept of emergence describes how complex systems exhibit properties not present in their individual components. Consciousness arising from the intricate interactions of neurons in the brain is a profound example of emergence. Scientific modeling involves creating simplified representations of complex systems or phenomena. These models help scientists understand and predict behavior, from climate patterns to the spread of diseases. The replication crisis refers to the concern that many scientific studies cannot be reproduced by independent researchers. This challenge underscores the need for transparent methodology and robust experimental design. Big data analytics has become a transformative tool in science. It enables researchers to find patterns and make discoveries from vast data sets, unlocking insights that were previously inaccessible. A scientific law describes an observed phenomenon in nature without necessarily explaining why it exists. It is often expressed as a mathematical relationship, a concise summary of empirical observations. The double-blind experiment is a scientific control method designed to minimize bias. Neither the participants nor the researchers know who is receiving a particular treatment, ensuring objectivity in results. The scientific method can be applied to social sciences as well. It uses empirical evidence to study human behavior and societies, bringing rigor to the understanding of complex social phenomena. The scientific revolution was a period in history when new ideas in physics, astronomy, biology, medicine, and chemistry transformed ancient and medieval views of nature. It marked a shift towards empirical observation and systematic experimentation. The scientific community is a global network of researchers who collaborate, share findings, and collectively advance knowledge. This collaborative spirit is essential for the progress of science. The principle of parsimony, often associated with Occam's razor, suggests that the simplest explanation that fits the evidence is usually the best one. It guides scientists in formulating theories that are both elegant and explanatory. The scientific principle of uniformitarianism posits that the same natural laws and processes that operate in the universe now have always operated in the universe in the past. This principle is fundamental to understanding geological and cosmic history. The development of scientific instruments like telescopes and microscopes has continually expanded the scope and precision of scientific inquiry. These tools extend our senses, revealing phenomena beyond our direct perception. The scientific method is not exclusive to laboratories. Field scientists use observation and experimentation in natural environments, studying ecosystems, geological formations, and celestial events. The scientific enterprise is inherently self-correcting. New evidence and theories constantly refine or overturn previous understandings, ensuring that knowledge evolves towards greater accuracy. The scientific pursuit of knowledge is a journey, not a destination. It's a continuous exploration that deepens our understanding and enriches our view of the universe. It is often driven by curiosity and the desire to understand the fundamental workings of the universe. This intrinsic motivation fuels countless hours of research and exploration. The scientific principle of causality states that every event has a cause. This forms the basis for much of scientific investigation, as researchers seek to identify the relationships between phenomena. The scientific endeavor relies heavily on mathematical frameworks to describe and predict natural phenomena. Mathematics provides the language and tools for precise scientific expression. Science often advances through paradigm shifts, where fundamental theories are replaced by new ones that better explain observed phenomena. These revolutionary moments reshape our understanding. The reproducibility crisis in science highlights the challenge of consistently replicating research findings across different studies. It underscores the importance of transparent methods and data sharing. Pseudoscience often mimics the outward appearance of science, but lacks empirical evidence, testability, or falsifiability. Distinguishing it from genuine science is a crucial aspect of scientific literacy. The peer review process is a cornerstone of scientific publishing. Experts evaluate research for validity and rigor before publication, maintaining the quality and integrity of scientific literature. Serendipity, or accidental discovery, has played a significant role in numerous scientific breakthroughs, from penicillin to Teflon. These unexpected findings often open entirely new avenues of research. The publish or perish culture in academia refers to the pressure on scientists to continuously publish research to maintain their careers. This dynamic can influence research priorities and practices. Citizen science projects engage the public in scientific research, contributing to data collection and analysis for various fields. This collaborative approach democratizes scientific inquiry. The philosophy of science explores the foundations, methods, and implications of science. It questions what constitutes scientific knowledge and how it is justified. Occam's razor, a principle in science, suggests that among competing hypotheses, the one with the fewest assumptions should be preferred. It encourages simplicity and elegance in scientific explanation. The scientific consensus represents the collective judgment, position, and opinion of the community of scientists in a particular field. It reflects a broad agreement based on the available evidence. Interdisciplinary science combines knowledge and methods from different scientific disciplines to address complex problems. Fields like astrobiology or bioinformatics exemplify this integrated approach. Science communication is the practice of informing, educating, sharing, and raising awareness of science-related topics to non-experts. It bridges the gap between scientific discovery and public understanding. The replication crisis in science refers to the difficulty of reproducing the results of many scientific experiments. This concern has led to calls for greater transparency and methodological rigor. Technoscience is a concept that emphasizes the intertwined nature of scientific research and technological development. They are often codependent, with advances in one driving the other. Scientific literacy refers to the public's understanding of scientific concepts and processes. It is essential for informed decision-making in an increasingly complex and technology-driven world. The null hypothesis is a foundational concept in inferential statistics. It states that there is no significant relationship between observed phenomena, providing a baseline for statistical testing. Scientific models are simplified representations of systems or phenomena. They are used to understand, predict, and explain complex processes, offering insights into how the natural world operates. The burden of proof in science typically rests on the person making a claim, especially if it challenges established scientific understanding. This ensures that new ideas are rigorously supported by evidence. Science is inherently self-correcting. New evidence and scrutiny can lead to the refinement or rejection of previous theories, ensuring that scientific knowledge continuously improves. The demarcation problem in the philosophy of science seeks to distinguish between science and non-science. It explores the criteria that define legitimate scientific inquiry. Scientific theories are well-substantiated explanations of some aspect of the natural world. They are based on a body of facts and repeatedly tested hypotheses, providing comprehensive frameworks for understanding. A scientific law describes an observed phenomenon, but does not explain why it occurs. Unlike a theory, laws are often concise mathematical statements of relationships. The Dunning-Kruger effect describes how people with low ability in a scientific task tend to overestimate their competence. This cognitive bias can hinder effective learning and critical assessment. Open science promotes transparency and accessibility in research. This includes open access to publications and data, fostering collaboration and accelerating discovery. The observer effect in science refers to how the act of observing a phenomenon can sometimes alter the phenomenon itself, particularly in the quantum realm. The funding bias in science refers to the potential for research outcomes to be influenced by the financial interests of the funding source. This highlights the importance of independent research. Meta-science, or research on research, studies how scientific research is conducted, reported, and evaluated. It aims to improve the efficiency and reliability of the scientific process. The file drawer problem in science refers to the bias created by studies with non-significant results being less likely to be published. This can lead to an incomplete picture of research findings. Scientific skepticism is an approach that questions the veracity of claims lacking empirical evidence. It promotes critical thinking and evidence-based reasoning. The precautionary principle in science suggests that if an action or policy has a suspected risk of causing harm, it should be avoided until its safety is established. Retraction in scientific publishing occurs when an article is withdrawn due to serious flaws, errors, or misconduct. This mechanism helps maintain the integrity of scientific literature. The scientific revolution refers to a period in the 16th to 18th centuries when new ideas in physics, astronomy, biology, and chemistry transformed society. It marked a fundamental shift in how knowledge was acquired. Inductive reasoning in science involves drawing general conclusions from specific observations. It moves from particular instances to broader generalizations. Deductive reasoning in science involves testing a general hypothesis against specific observations. It moves from general principles to specific predictions. The Nobel Prize is an internationally recognized award for outstanding achievements in physics, chemistry, physiology or medicine, literature, and peace. It celebrates significant contributions to human knowledge and welfare. Science is a global endeavor, with researchers from diverse cultures contributing to its advancement. Collaboration across borders is increasingly vital for addressing complex challenges. The replication crisis in science underscores the importance of rigorous methodology and transparent reporting. It prompts a critical examination of research practices. Science thrives on collaboration, with many major discoveries resulting from the work of large, international teams. Collective effort often leads to breakthroughs that individual efforts cannot achieve. The Hawthorne effect in science describes how subjects of an experiment may improve their performance in response to being observed. This highlights the psychological aspects of research. The placebo effect is a phenomenon where a person experiences a perceived improvement in health due to a non-therapeutic intervention. It demonstrates the powerful influence of expectation and belief. Science fiction often inspires real-world scientific research and technological development. Imagining future possibilities can spark innovation and guide scientific inquiry. The scientific enterprise is a complex ecosystem involving researchers, institutions, funding bodies, publishers, and the public. All play a role in the advancement of knowledge. Science is constantly evolving, with new discoveries challenging and refining existing knowledge. This dynamic process ensures that our understanding of the universe continues to deepen. The scientific community plays a crucial role in validating research through peer review and open discourse. This collective scrutiny ensures the quality and reliability of scientific findings. The scientific revolution was not a single event, but a gradual shift in thought that began in the 16th century, emphasizing empirical evidence over dogma. It laid the foundation for modern science. Interdisciplinary science, like astrobiology or bioinformatics, combines multiple scientific fields to address complex questions. This integrated approach often yields novel insights. The peer review process is a fundamental mechanism in science where experts evaluate research before publication to ensure quality and validity. It is a cornerstone of scientific integrity. Theoretical science constructs mathematical models and conceptual frameworks to explain phenomena, often preceding experimental verification. It provides the intellectual scaffolding for empirical research. Citizen science projects involve public participation in data collection and analysis, contributing to large-scale scientific research. This engagement fosters scientific literacy and discovery. The concept of paradigm shifts in science, introduced by Thomas Kuhn, describes fundamental changes in the basic concepts and experimental practices of a scientific discipline. These shifts mark significant advancements. Metascience, or the science of science, studies scientific research itself, aiming to improve its quality and efficiency. It applies scientific methods to understand the scientific process. The null hypothesis is a core concept in scientific experimentation, stating there is no significant relationship between observed phenomena. It serves as a starting point for statistical analysis. Reproducibility is a cornerstone of scientific integrity, meaning other researchers should be able to replicate an experiment and achieve similar results. It ensures the reliability of findings. Occam's razor, a principle often used in science, suggests that among competing hypotheses, the one with the fewest assumptions should be selected. It promotes simplicity and clarity in scientific explanation. Epistemology, a branch of philosophy, critically examines the nature of scientific knowledge, its acquisition, and its limitations. It delves into the very essence of what we know and how we know it. The double-blind study is a scientific method where neither the participants nor the researchers know who is receiving a particular treatment, minimizing bias. This design enhances the objectivity of results. The butterfly effect in chaos theory illustrates how small localized changes in a complex system can have large effects elsewhere, challenging deterministic scientific prediction. It highlights the inherent unpredictability of certain systems. The gold standard in scientific research often refers to randomized controlled trials, RCTs, due to their ability to minimize bias. These trials are highly valued for their rigor in evaluating interventions. Pseudoscience refers to claims, beliefs, or practices presented as scientific but lacking empirical evidence or testability. It is important to distinguish it from genuine scientific inquiry. The observer effect in science describes how the act of observing a phenomenon can sometimes alter the phenomenon itself, particularly in quantum mechanics. This fundamental aspect challenges our classical intuitions. The scientific literacy movement aims to equip the public with the knowledge and understanding of scientific concepts and processes. It empowers individuals to engage with scientific issues and make informed decisions. The null result in an experiment where no significant effect is found is still valuable scientific data, challenging existing hypotheses. It informs future research directions and refines understanding. The scientific community is a global network of researchers, institutions, and journals that collectively advance human knowledge. This collaborative ecosystem drives scientific progress. The precautionary principle in science suggests that if an action or policy has a suspected risk of causing harm to the public or environment, in the absence of scientific consensus that the action or policy is harmful, the burden of proof that it is not harmful falls on those taking the action. It is a guiding principle for responsible innovation. The scientific journal emerged in the 17th century as a primary means for scientists to share and validate their findings. These publications are central to the dissemination of new knowledge. The scientific method is a cyclical process where new discoveries often lead to new questions and further investigation. This continuous loop of inquiry and discovery is the essence of scientific progress. As we conclude our journey through the vast landscape of science, we rest with the understanding that the quest for knowledge is an endless, evolving, and deeply human endeavor. The scientific method, with its structured approach to inquiry, has illuminated countless mysteries. It provides a framework for understanding the universe, from the smallest particles to the grandest cosmic structures. This systematic pursuit of knowledge has reshaped our world. From the foundational principles of physics to the intricate workings of biology, each discipline contributes to a broader tapestry of understanding. These fields are often interconnected, their discoveries influencing and enriching one another. Consider the flow of water in a river, a gentle current moving steadily onward. This current represents the continuous stream of scientific discovery, always advancing, always exploring new territories of thought. The study of fluid dynamics, for instance, delves into the behavior of liquids and gases. It examines how these substances move, how they interact with solid surfaces, and how forces like pressure and viscosity affect their flow. Engineers apply these principles to design efficient pipelines, aerodynamic aircraft, and even the subtle curves of a boat's hull. Understanding fluid dynamics is crucial for many practical applications. Oceanographers use fluid dynamics to model ocean currents, predicting their paths and understanding their role in global climate patterns. The movement of vast water masses influences weather systems across continents. Atmospheric scientists employ similar principles to forecast weather, tracking the movement of air masses, fronts, and storm systems. The atmosphere is a complex fluid, constantly in motion. Even the human body relies on fluid dynamics. The circulation of blood through arteries and veins, the flow of air into and out of the lungs, these are all governed by the same fundamental laws. The heart acts as a pump, creating pressure differences that propel blood throughout the circulatory system. The intricate network of vessels ensures that every cell receives oxygen and nutrients. Blood itself is a complex fluid, a suspension of cells and plasma. Its viscosity can change, affecting the ease with which it flows. These properties are vital for maintaining health. Beyond the macroscopic world, the principles of flow extend to the microscopic. Within cells, various molecules move and interact, driven by diffusion and active transport mechanisms. These intercellular currents are essential for life, orchestrating processes like protein synthesis and energy production. The cell is a bustling city of molecular activity. The concept of a current, a steady, directed movement, appears in many scientific contexts. It is a unifying theme, whether we speak of water, air, electricity, or information. Electrical currents, for example, are the flow of charged particles, typically electrons, through a conductor. This invisible flow powers our modern world, lighting our homes and running our devices. The discovery of electricity and its properties revolutionized technology. From simple circuits to complex microprocessors, the control of electron flow is fundamental. Superconductors, materials that conduct electricity with zero resistance at very low temperatures, represent an extreme example of efficient current flow. They hold promise for future technologies. The flow of information is another kind of current. In computing, data moves through networks and processors, a continuous stream of bits and bytes. This digital current connects us globally. Neuroscience explores the electrical and chemical currents within the brain. Neurons communicate through electrochemical signals, creating the intricate patterns of thought and consciousness. These neural currents are incredibly complex, forming vast networks that process sensory input, generate motor commands, and store memories. The brain is an astonishing biological computer. The study of waves also involves a form of current, the propagation of energy through a medium. Sound waves travel through air, water, or solids, carrying auditory information. Light waves, electromagnetic radiation, travel through the vacuum of space, bringing us the warmth of the sun and the distant glow of stars. They are a current of pure energy. Seismic waves, generated by earthquakes, travel through the Earth's interior, providing scientists with clues about its structure. These powerful currents reveal hidden depths. The gentle current of scientific progress itself is a continuous flow of ideas, experiments, and discoveries. Each new finding builds upon previous knowledge, creating a deeper understanding. This cumulative nature of science means that even small contributions can have far-reaching effects over time. A single observation can spark a new line of inquiry. The development of theories often involves a gradual accumulation of evidence, like a river slowly carving its path through stone. Over time, these theories become more refined and robust. Consider the theory of evolution by natural selection, a cornerstone of modern biology. It emerged from decades of observation and analysis by countless scientists. Darwin's initial insights, combined with later discoveries in genetics and molecular biology, have painted a comprehensive picture of life's diversity and adaptation. The theory of plate tectonics, explaining the movement of Earth's continents, also developed over many years. Early ideas about continental drift were initially met with skepticism. However, as more evidence emerged from seafloor spreading, paleomagnetism, and seismic data, the theory gained widespread acceptance. It transformed our understanding of Earth's dynamics. These major scientific theories are like broad, deep currents, shaping the landscape of our knowledge. They provide powerful explanatory frameworks for vast amounts of data. Even in the realm of mathematics, there is a sense of flow. Mathematical proofs often build upon previous theorems, creating a logical chain of reasoning. The development of calculus, for example, provided tools to understand rates of change and accumulation, essential for describing continuous processes like fluid flow or planetary motion. The concept of infinity, a vast and boundless idea, can be thought of as an endless current, always expanding, always beyond complete grasp. It challenges our intuition. In astronomy, the expansion of the universe is a grand current, carrying galaxies away from each other over cosmic timescales. This expansion continues, ever outward. The formation of stars and galaxies from vast clouds of gas and dust is another slow, majestic current, unfolding over billions of years. Gravity draws matter together, shaping cosmic structures. Dark matter and dark energy, mysterious components of the universe, represent unseen currents influencing its evolution. Their nature remains one of science's greatest puzzles. The search for extraterrestrial life, a quest spanning disciplines, is a current of curiosity, pushing us to explore beyond our planet. It asks fundamental questions about our place in the cosmos. The gentle current of scientific inquiry encourages patience and persistence. Discoveries are not always sudden breakthroughs, but often the result of steady, meticulous work. It is a process of asking questions, designing experiments, analyzing data, and then asking more questions. Each step is a small ripple in the larger current. The act of observation itself is a fundamental current in science. Careful, unbiased observation forms the bedrock of empirical knowledge. From Galileo's observations of the moon and planets through his telescope to modern astronomers using vast observatories, seeing is often the first step to understanding. Microscopy allows us to observe the intricate details of cells and microorganisms, revealing hidden worlds within worlds. These observations expand our perception. The development of new instruments and technologies often creates new currents of discovery, enabling us to see, measure, and analyze phenomena previously inaccessible. Particle accelerators, for example, allow physicists to probe the fundamental constituents of matter, revealing the smallest currents of the universe. Space probes carry instruments to distant planets, sending back data that transforms our understanding of other worlds. These robotic explorers extend our senses across vast distances. The sharing of knowledge through scientific publications and conferences ensures that the current of information flows freely among researchers worldwide. Collaboration is key. This open exchange allows ideas to be tested, refined, and built upon by a global community of scholars. It accelerates the pace of discovery. The scientific community itself is a vast interconnected network, a current of human intellect working together to unravel the universe's complexities. Each individual scientist contributes their unique perspective and expertise, adding to the collective understanding. It is a shared journey of exploration. The gentle current of knowledge continues to flow, carrying us forward into new understandings. It is a journey without end, always revealing more. As we rest with these thoughts, we acknowledge the continuous unfolding nature of scientific endeavor. It is a steady, reassuring movement. The quest for knowledge is a calm and persistent current, ever present, ever moving. It offers a sense of continuity and progress. This quiet current of understanding flows onward, carrying with it the promise of new insights and deeper comprehension. It is a journey of peace. The quiet current of understanding flows onward, carrying with it the promise of new insights and deeper comprehension. It is a journey of peace. This journey often begins with observation, careful looking, noticing patterns. A scientist might spend years observing a single phenomenon, like the slow growth of a crystal or the subtle shift of a star's light. These observations form the bedrock of scientific inquiry. They are the first whispers of a new idea. From these whispers, questions emerge. Why does this happen? How does it work? These questions guide the path forward. They are not rushed. They are pondered, considered from many angles. Sometimes the answer is not immediately apparent. Years may pass. Generations of scientists may contribute, each adding a small piece to the larger mosaic. The process is patient. It respects the complexity of the natural world. It acknowledges that understanding unfolds gradually, like the opening of a rare bloom. Each petal reveals a new layer, a new detail. The scientific method itself is a path of quiet steps. Hypothesis, experiment, analysis, conclusion. Each step is deliberate, measured. It is a way of walking softly through the unknown, seeking truth without disturbance. The pursuit of knowledge is a gentle exploration. It respects the silence of the universe. It listens for its subtle harmonies. This quiet listening continues, always. The universe holds its breath, a profound, silent calm. The universe whispers its ancient secrets now. The universe whispers its ancient secrets now, a cosmic murmur echoing through the vast expanse of space and time, revealing the intricate tapestry woven by the fundamental forces and particles that govern all existence. This grand narrative of science unfolds through the patient accumulation of observations, each piece of data a tiny star in the constellation of human understanding, guiding us through the darkness of ignorance towards the illuminating dawn of knowledge. Consider the elegant dance of subatomic particles, the quarks and leptons that constitute the very building blocks of matter. Their interactions mediated by force-carrying bosons, like photons for electromagnetism, gluons for the strong nuclear force, and W and Z bosons for the weak nuclear force, all described with astonishing precision by the Standard Model of particle physics. This model, a cornerstone of modern physics, categorizes these elementary particles and explains how they interact, providing a comprehensive framework for understanding the universe at its most fundamental level. Though it does not yet incorporate gravity or account for dark matter and dark energy, which remain profound mysteries. The journey into the quantum realm reveals a universe far stranger and more counterintuitive than our everyday experience suggests, where particles can exist in multiple states simultaneously, a phenomenon known as superposition, and become entangled, meaning their fates are inextricably linked, regardless of the distance separating them, challenging our classical notions of reality. Quantum mechanics, developed in the early 20th century by brilliant minds such as Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, fundamentally altered our perception of the universe, demonstrating that energy and matter are not continuous but exist in discrete packets called quanta, forever changing the landscape of scientific inquiry. This revolutionary theory underpins much of modern technology, from lasers and transistors to magnetic resonance imaging, MRI, and quantum computing, illustrating the profound practical applications that can arise from abstract theoretical breakthroughs. Moving beyond the subatomic, we encounter the vastness of the cosmos, where astrophysics and cosmology meticulously piece together the history and future of the universe, from the fiery genesis of the Big Bang to the eventual fate of stars and galaxies. The Big Bang theory, supported by a wealth of observational evidence, including the cosmic microwave background radiation, a faint afterglow of the universe's infancy, and the observed expansion of the universe, describes the origin and evolution of the cosmos from an extremely hot, dense state approximately 13.8 billion years ago. Telescopes, both ground-based and orbiting, act as our eyes on the universe, collecting light and other forms of electromagnetic radiation from distant galaxies, nebulae, and exoplanets, allowing astronomers to infer their composition, temperature, velocity, and distance, thereby painting an ever clearer picture of our cosmic neighborhood and beyond. The discovery of exoplanets, planets orbiting stars other than our Sun, has revolutionized our understanding of planetary formation and the potential for life elsewhere in the universe, with thousands now identified through various detection methods, like the transit method and radial velocity method, some even residing in the habitable zones of their parent stars. Geology, a foundational earth science, delves into the solid earth, its rocks, minerals, and the processes that have shaped its surface and interior over billions of years, from the slow creep of tectonic plates to the explosive power of volcanic eruptions and the erosive force of water and wind. The theory of plate tectonics, a unifying paradigm in earth sciences, explains the large-scale motions of Earth's lithosphere, the rigid outer shell, which is broken into several large plates that slowly glide over the mantle, driving phenomena such as earthquakes, mountain building, and the formation of ocean basins. Paleontology, often intertwined with geology, meticulously unearths the fossilized remains of ancient life, providing invaluable insights into the evolutionary history of species, the changing environments of the past, and the grand narrative of life's diversification and extinction events across geological epochs. The study of stratigraphy, the layering of sedimentary rocks, allows geologists and paleontologists to reconstruct chronological sequences of events, correlating rock units across vast distances and establishing a timeline for Earth's dynamic history, revealing profound shifts in climate, geography, and biodiversity. Climatology and meteorology focus on the Earth's atmosphere, studying weather patterns, climate systems, and the complex interactions between the atmosphere, oceans, land surfaces, and ice sheets, which collectively determine our planet's climate. The Earth's climate system is a delicate balance of incoming solar radiation and outgoing thermal radiation, influenced by greenhouse gases like carbon dioxide and methane, which trap heat in the atmosphere. A natural process essential for life, but now intensified by human activities, leading to concerns about anthropogenic climate change. Oceanography explores the vast and mysterious marine environments, from the shallow, sunlit waters of coral reefs teeming with biodiversity to the crushing depths of the abyssal plains and hydrothermal vents, which support unique chemosynthetic ecosystems independent of sunlight. The global ocean conveyor belt, a complex system of deep ocean currents driven by temperature and salinity differences, thermohaline circulation, plays a crucial role in redistributing heat around the planet, influencing regional climates and marine ecosystems on a vast scale. Biology, the science of life, encompasses an astonishing array of disciplines, from molecular biology, investigating the intricate machinery within cells, to ecology, studying the interactions of organisms with their environment and with each other. Genetics, a core branch of biology, explores heredity and variation in living organisms, focusing on genes, the fundamental units of inheritance, and their role in transmitting traits from one generation to the next. A field revolutionized by the discovery of the double helix structure of DNA by James Watson and Francis Crick. The central dogma of molecular biology describes the flow of genetic information from DNA to RNA to protein, a fundamental process that underpins all life, dictating the synthesis of proteins that perform virtually all cellular functions and constitute the structural components of organisms. Evolutionary biology, founded on Charles Darwin's theory of natural selection, explains the diversity of life on Earth, proposing that species gradually change over time through a process where individuals with advantageous traits are more likely to survive and reproduce, passing those traits to their offspring, leading to the gradual adaptation of populations to their environments. Ecology investigates the complex web of relationships between living organisms and their physical surroundings, examining how energy flows through ecosystems, how nutrients are cycled, and how populations and communities interact, forming intricate food webs and symbiotic associations. Biodiversity, the variety of life at all levels, from genes to ecosystems, is a critical focus of ecological study, as it underpins ecosystem stability, resilience, and the provision of essential ecosystem services, such as clean air and water, pollination, and climate regulation. Microbiology, a specialized field, delves into the world of microscopic organisms, bacteria, viruses, fungi, and protists, many of which are invisible to the naked eye, but play indispensable roles in nutrient cycling, decomposition, disease, and biotechnology, forming the vast majority of Earth's biomass and genetic diversity. Immunology, a fascinating branch of biology and medicine, explores the intricate defense mechanisms of the immune system, which protects the body from pathogens and foreign substances through a complex interplay of cells, tissues, and organs, recognizing and neutralizing threats while maintaining tolerance to self-components. Neuroscience, a rapidly expanding field, seeks to unravel the mysteries of the brain and nervous system, investigating how neurons communicate, how memories are formed, how emotions are processed, and how consciousness arises from the intricate electrical and chemical signaling within neural networks. The human brain, a marvel of biological engineering, contains billions of neurons forming trillions of connections, constantly processing sensory information, coordinating movements, regulating physiological functions, and enabling complex cognitive abilities like language, reasoning, and creativity. Cognitive science, an interdisciplinary field drawing from psychology, artificial intelligence, linguistics, philosophy, and neuroscience, explores the nature of mind and intelligence, investigating how humans and other intelligent systems perceive, learn, remember, and make decisions. Psychology, a broad scientific discipline, systematically studies behavior and mental processes, employing empirical methods to understand human cognition, emotion, personality, social interactions, and developmental changes across the lifespan, aiming to alleviate psychological distress and promote well-being. Chemistry, the central science, bridges physics and biology, investigating the composition, structure, properties, and reactions of matter, from the simplest atoms to complex macromolecules. Organic chemistry focuses specifically on carbon-containing compounds, which form the basis of all known life, exploring their vast diversity, synthesis, and reactions, a field crucial for pharmaceuticals, polymers, and petrochemicals. Inorganic chemistry deals with compounds that do not primarily contain carbon-hydrogen bonds, encompassing metals, minerals, and many industrial catalysts, playing a vital role in materials science, environmental chemistry, and geochemistry. Physical chemistry applies principles of physics to chemical systems, studying thermodynamics, kinetics, quantum mechanics, and spectroscopy to understand the fundamental forces and energy changes involved in chemical reactions and the properties of matter at the molecular level. Analytical chemistry develops and applies methods to measure the chemical composition of substances, identifying and quantifying components in various samples, which is essential for quality control, environmental monitoring, forensic science, and medical diagnostics. Materials science and engineering, an interdisciplinary field, focuses on discovering and designing new materials with specific properties, understanding their structure at atomic and molecular levels, and predicting their performance for various applications, from advanced ceramics and composites to semiconductors and biomaterials. Nanotechnology, a cutting-edge area, manipulates matter on an atomic and molecular scale, typically ranging from 1 to 100 nanometers, to create novel materials and devices with unprecedented properties, promising breakthroughs in medicine, electronics, energy, and manufacturing. Biomedical engineering applies engineering principles and design concepts to medicine and biology for healthcare purposes, such as developing medical devices, diagnostic equipment, therapeutic technologies, and artificial organs, thereby improving human health and quality of life. Robotics, a field at the intersection of engineering, computer science, and artificial intelligence, designs, constructs, operates, and applies robots, autonomous machines capable of performing tasks in various environments, from manufacturing and exploration to healthcare and domestic assistance. Computer science, a foundational discipline of the information age, explores computation, algorithms, data structures, programming languages, and the design of computer systems, underpinning virtually every aspect of modern technology and scientific research. Artificial intelligence, a subfield of computer science, aims to create intelligent machines that can perceive their environment, learn from experience, reason, solve problems, and make decisions, mimicking or exceeding human cognitive abilities, with applications ranging from natural language processing and image recognition to autonomous vehicles and scientific discovery. Data science, an interdisciplinary field, extracts knowledge and insights from structured and unstructured data using scientific methods, processes, algorithms, and systems, transforming raw data into actionable intelligence for decision-making in business, science, and government. Bioinformatics, a specialized area, combines computer science, statistics, and molecular biology to analyze and interpret large biological datasets, such as genomic sequences, protein structures, and gene expression profiles, accelerating research in genetics, drug discovery, and personalized medicine. The scientific method, a systematic approach to inquiry, is not a rigid dogma, but a flexible framework that guides researchers in formulating testable hypotheses, designing experiments to gather empirical evidence, analyzing data with statistical rigor, and drawing conclusions that are open to revision based on new findings. Peer review, a critical component of the scientific process, involves the evaluation of scientific work by other experts in the same field, ensuring the quality, validity, and originality of research before publication, thereby maintaining the integrity of scientific knowledge. Scientific theories, such as the theory of evolution, the theory of general relativity, or the germ theory of disease, are not mere guesses, but well-substantiated explanations of some aspect of the natural world, based on a vast body of evidence, repeatedly tested and confirmed through observation and experimentation, representing the pinnacle of scientific understanding. The continuous refinement of scientific instruments, from electron microscopes and particle accelerators to space telescopes and DNA sequencers, constantly pushes the boundaries of what we can observe and measure, leading to new discoveries and deeper insights into the universe. The history of science is a testament to human curiosity and ingenuity, marked by paradigm shifts that fundamentally altered our understanding of the world. From the Copernican revolution, placing the sun at the center of the solar system, to Newton's laws of motion and universal gravitation, which unified terrestrial and celestial mechanics. The Enlightenment era fostered a spirit of rational inquiry and empirical observation, laying the groundwork for modern scientific disciplines and promoting the idea that knowledge could be systematically acquired and applied to improve the human condition. The Industrial Revolution, driven by scientific discoveries in thermodynamics, chemistry, and engineering, transformed societies, leading to unprecedented technological advancements and economic growth, albeit with significant social and environmental consequences that continue to be addressed through ongoing scientific and technological innovation. The scientific community, a global network of researchers, collaborators, and educators, fosters the open exchange of ideas, methodologies, and results, accelerating the pace of discovery and ensuring that scientific progress benefits all of humanity. Ethical considerations are paramount in scientific research, guiding the responsible conduct of experiments, the protection of research participants, the humane treatment of animals, and the transparent reporting of results, ensuring that scientific advancements are pursued with integrity and for the benefit of society. The interplay between basic research, which seeks to expand fundamental knowledge without immediate practical application, and applied research, which aims to solve specific problems, is crucial for scientific progress, as fundamental discoveries often lay the groundwork for future technological innovations and societal benefits. Science education, from primary school to advanced university programs, is vital for nurturing critical thinking skills, fostering scientific literacy, and inspiring the next generation of scientists and innovators who will continue the quest for knowledge and address the complex challenges facing our planet. The interdisciplinary nature of modern science means that breakthroughs often occur at the interfaces between traditional fields, requiring collaboration among experts from diverse backgrounds to tackle complex problems that transcend single disciplines. The pursuit of scientific understanding is an ongoing, dynamic process, characterized by continuous questioning, rigorous testing, and a willingness to revise existing ideas in light of new evidence, embodying a spirit of intellectual humility and an unwavering commitment to truth. This methodical exploration of the universe, whether peering into the smallest particles or gazing at the farthest galaxies, reveals an underlying order and beauty, a profound elegance in the laws that govern everything from the growth of a single cell to the majestic spiral of a galaxy. Each discovery, no matter how small, contributes to the grand mosaic of knowledge, slowly but surely illuminating the intricate mechanisms of the natural world and our place within it, a testament to the enduring power of human intellect and curiosity. The quiet dedication of scientists working in laboratories, observatories, and field stations around the globe, patiently gathering data and meticulously analyzing observations, continuously expands the boundaries of what is known, transforming the unknown into the understood. This gentle, persistent inquiry, driven by an insatiable desire to comprehend the universe, continues to unfold its wonders, one careful step at a time, revealing the profound and intricate harmonies that resonate throughout all existence. The profound and intricate harmonies that resonate throughout all existence are often deciphered through the rigorous application of the scientific method, a systematic approach to inquiry that forms the bedrock of all empirical investigation, beginning with careful observation and the formulation of testable hypotheses. This iterative process, far from being a rigid set of steps, is a dynamic and adaptable framework that encourages curiosity, critical thinking, and a constant questioning of assumptions, allowing for the refinement and even complete overturning of established theories in the face of new evidence. From the earliest stargazers charting celestial movements to modern particle physicists probing the fundamental constituents of matter, the scientific method has provided humanity with an unparalleled tool for understanding the natural world, moving beyond anecdotal evidence and superstitious beliefs to establish verifiable knowledge. One of the most compelling aspects of scientific discovery lies in its historical evolution, tracing a path from ancient philosophical inquiries to the highly specialized and interconnected disciplines of today, each era building upon the insights and sometimes the errors of its predecessors. In ancient Mesopotamia, for instance, careful astronomical observations were meticulously recorded on clay tablets, primarily for calendrical and astrological purposes. But these detailed records laid foundational data for later mathematical astronomy, demonstrating an early form of empirical data collection. Similarly, ancient Egyptian medicine, though intertwined with religious practices, developed sophisticated surgical techniques and pharmacological knowledge, documenting treatments for various ailments in papyri like the Edwin Smith Papyrus, which describes anatomical observations and rational approaches to injury management. Classical Greek philosophy, particularly the works of Aristotle, introduced systematic classification and logical deduction, profoundly influencing Western thought for centuries. Even though much of his natural philosophy relied on qualitative observation rather than quantitative experimentation, establishing a framework for thinking about the natural world that emphasized reason and categorization. Aristotle's extensive writings on biology, physics, and metaphysics attempted to explain phenomena through teleological principles, where everything has an inherent purpose, a concept that would later be challenged by mechanistic explanations of the universe. The Hellenistic period, following Alexander the Great, saw the flourishing of scientific centers like the Library of Alexandria, where scholars such as Eratosthenes accurately calculated the Earth's circumference using geometric principles and observational data, a remarkable feat of ancient geodesy. Euclid systematized geometry in his Elements, creating a deductive system that served as a model for mathematical rigor for over 2 millennia, demonstrating the power of axiomatic reasoning in establishing irrefutable truths. During the Islamic Golden Age, scholars preserved, translated, and expanded upon Greek and Roman knowledge, making significant original contributions in fields ranging from astronomy and mathematics to medicine and optics, often integrating empirical observation with theoretical frameworks. Figures like Ibn al-Haytham, known as Al-Hazan in the West, revolutionized optics through experimental investigations, demonstrating that vision occurs when light enters the eye rather than being emitted by it, and his Book of Optics laid the groundwork for modern optical theory and the scientific method itself, emphasizing controlled experiments and mathematical analysis. Al-Biruni, another polymath of this era, conducted pioneering work in geodesy, cartography, and pharmacology, developing precise methods for measuring Earth's radius and describing the properties of various minerals and drugs, showcasing a holistic approach to scientific inquiry. The European Renaissance marked a pivotal transition as a renewed interest in classical learning, combined with technological innovations like the printing press, facilitated the widespread dissemination of knowledge, setting the stage for the scientific revolution. Nicolaus Copernicus, challenging the geocentric model that had prevailed for over 1400 years, proposed a heliocentric system where the Earth and other planets revolved around the Sun, a radical idea that initiated a profound shift in cosmological understanding. Although his model still retained perfect circular orbits, this paradigm shift was further propelled by Johannes Kepler, who, using Tycho Brahe's meticulous astronomical data, mathematically demonstrated that planets move in elliptical orbits, not perfect circles, thereby refining Copernicus's model and establishing the laws of planetary motion, providing a quantitative description of celestial mechanics. Galileo Galilei, often considered the father of observational astronomy and modern physics, utilized the newly invented telescope to make groundbreaking discoveries, observing the phases of Venus, the moons of Jupiter, and the craters on the Moon, providing empirical evidence that strongly supported the heliocentric model and challenging Aristotelian cosmology. His experiments with falling bodies, demonstrating that objects of different masses fall at the same rate in a vacuum, laid the foundation for classical mechanics, emphasizing the importance of quantitative measurement and controlled experimentation over purely philosophical reasoning. The work of these pioneers culminated in Isaac Newton's monumental synthesis, articulated in his Philosophia Naturalis Principia Mathematica, where he formulated the laws of motion and universal gravitation, unifying terrestrial and celestial mechanics under a single explanatory framework, thereby providing a comprehensive mathematical description of the physical universe that dominated scientific thought for centuries. Newton's development of calculus, alongside Gottfried Wilhelm Leibniz, provided the mathematical tools necessary to describe continuous change in motion, becoming indispensable for subsequent scientific and engineering advancements. The Enlightenment further championed reason and empirical evidence, leading to significant advancements in chemistry and biology. Antoine Lavoisier, through meticulous quantitative experiments, established the law of conservation of mass and identified oxygen's role in combustion and respiration, effectively overturning the phlogiston theory and laying the foundation for modern chemistry, transforming it from an alchemical pursuit into a rigorous scientific discipline. Carl Linnaeus developed a hierarchical system for classifying organisms, known as binomial nomenclature, which provided a standardized and systematic way to organize the diversity of life, facilitating communication and understanding among naturalists worldwide. The 19th century witnessed an explosion of scientific progress across numerous fields, driven by industrialization and a growing emphasis on scientific education and research institutions. John Dalton proposed the atomic theory, suggesting that matter is composed of indivisible atoms with distinct masses, providing a quantitative basis for chemical reactions and paving the way for understanding molecular structures. Michael Faraday's groundbreaking experiments in electromagnetism demonstrated the interrelationship between electricity and magnetism, leading to the development of electric motors and generators, and laying the foundation for modern electrical engineering and Maxwell's equations. Charles Darwin's theory of evolution by natural selection, presented in On the Origin of Species, provided a compelling mechanism for the diversity and adaptation of life, revolutionizing biology and challenging prevailing creationist views, emphasizing the gradual accumulation of advantageous traits over vast spans of time. Gregor Mendel's work on pea plants, though largely unrecognized during his lifetime, established the fundamental principles of heredity, demonstrating how traits are passed from one generation to the next through discrete units, now known as genes, thereby founding the science of genetics. Louis Pasteur's work on germ theory disproved spontaneous generation and established that microorganisms cause diseases and spoilage, leading to revolutionary advancements in medicine, public health, and food preservation, including pasteurization and vaccine development. The early 20th century brought about another scientific revolution, challenging the classical Newtonian worldview with the advent of relativity and quantum mechanics. Albert Einstein's theories of special and general relativity fundamentally altered our understanding of space, time, gravity, and the universe, demonstrating that space and time are not absolute, but relative to the observer's motion, and that gravity is a curvature of space-time caused by mass and energy. Max Planck introduced the concept of energy quantization, proposing that energy is emitted and absorbed in discrete packets called quanta, thereby initiating quantum mechanics, which describes the behavior of matter and energy at the atomic and subatomic levels, a realm where classical physics breaks down. Niels Bohr developed a quantum model of the atom, explaining the stability of electron orbits and the emission spectra of elements, providing a crucial step towards understanding atomic structure. Werner Heisenberg's uncertainty principle demonstrated that certain pairs of physical properties, like position and momentum, cannot both be known with arbitrary precision simultaneously, introducing a fundamental limit to measurement in the quantum realm. Erwin Schrödinger formulated the wave equation, which describes how the quantum state of a physical system changes over time, providing a mathematical framework for quantum mechanics that has been incredibly successful in predicting experimental outcomes. These quantum theories led to the development of technologies like lasers, transistors, and nuclear energy, profoundly impacting modern society, from computing and communications to medicine and energy production. The discovery of the structure of DNA by James Watson, Francis Crick, Rosalind Franklin, and Maurice Wilkins in the mid-20th century revealed the double helix, the molecular basis of heredity, opening up the field of molecular biology and biotechnology, which has transformed medicine, agriculture, and forensics. The subsequent Human Genome Project, culminating in the mapping of the entire human genetic code, has provided unprecedented insights into human biology, disease, and evolution, paving the way for personalized medicine and gene therapies. Astronomy and cosmology have also undergone dramatic transformations, moving from a static view of the universe to one of dynamic expansion and evolution. Edwin Hubble's observations in the 1920s demonstrated that the universe is expanding and that galaxies are moving away from each other, providing the first observational evidence for the Big Bang Theory, which posits that the universe originated from an extremely hot, dense state. The discovery of the cosmic microwave background radiation in 1964 by Arno Penzias and Robert Wilson provided strong corroborating evidence for the Big Bang, representing the residual heat from the early universe. Modern cosmology continues to explore the mysteries of dark matter and dark energy, which constitute the vast majority of the universe's mass and energy, but remain largely unknown, driving new theoretical models and observational campaigns. The development of powerful telescopes, both ground-based and space-based, like the Hubble Space Telescope and the James Webb Space Telescope, has allowed astronomers to peer further back in time and observe the formation of the first stars and galaxies, revealing the universe's evolutionary history in unprecedented detail. The field of materials science, a multidisciplinary area that investigates the properties of matter and its applications, has led to the development of countless new materials with tailored characteristics, from advanced ceramics and polymers to superconductors and nanomaterials, revolutionizing industries from aerospace to medicine. Nanotechnology, which involves manipulating matter on an atomic and molecular scale, promises to create materials with novel properties and has applications in electronics, medicine, and energy, pushing the boundaries of what is technologically possible. Computer science, emerging from the theoretical work of Alan Turing and John von Neumann, has transformed every aspect of modern life, from communication and information processing to scientific research and artificial intelligence, providing powerful tools for modeling complex systems and analyzing vast data sets. The development of algorithms and computational methods has enabled scientists to simulate phenomena that are too complex or too dangerous to study directly, such as climate change models, drug interactions, and stellar evolution. Environmental science, a relatively newer interdisciplinary field, integrates biology, chemistry, physics, and geology to study the natural environment and the impact of human activities upon it, addressing critical issues like climate change, biodiversity loss, and pollution. This field relies heavily on complex data analysis, remote sensing technologies, and ecological modeling to understand interconnected systems and propose sustainable solutions, emphasizing the intricate balance of Earth's ecosystems. The study of climate change, for instance, involves analyzing ice core data, atmospheric gas concentrations, ocean currents, and global temperature records to understand past and present climatic patterns and predict future scenarios, demonstrating the power of interdisciplinary scientific collaboration. Neuroscience, the study of the nervous system, has made incredible strides in understanding the complexities of the brain, from the molecular mechanisms of neuronal communication to the neural correlates of consciousness, employing techniques like functional magnetic resonance imaging, fMRI, and electroencephalography, EEG, to map brain activity. This research not only sheds light on human cognition, emotion, and behavior, but also offers hope for treating neurological and psychiatric disorders, pushing the boundaries of our understanding of the mind itself. Cognitive science, an interdisciplinary field that combines neuroscience, psychology, linguistics, philosophy, and computer science, investigates the nature of thought, perception, memory, and language, seeking to understand the mechanisms of intelligence, both natural and artificial. The very nature of scientific progress is often characterized by periods of normal science, where a dominant paradigm guides research, punctuated by scientific revolutions or paradigm shifts, as described by Thomas Kuhn, where existing frameworks are challenged and eventually replaced by new ones that better explain observed phenomena. This dynamic interplay between established knowledge and revolutionary ideas ensures that science remains a self-correcting and evolving enterprise, constantly refining its understanding of the universe. The peer review process, where scientific manuscripts are critically evaluated by other experts in the field before publication, serves as a crucial gatekeeper for quality and validity, ensuring that research meets rigorous standards of methodology and analysis, fostering transparency and accountability within the scientific community. Furthermore, the increasing interconnectedness of scientific disciplines, often referred to as interdisciplinary research, allows for novel insights and solutions to complex problems that transcend traditional boundaries, fostering collaboration between physicists and biologists, chemists and computer scientists, and many other combinations. This collaborative spirit extends globally, with international research collaborations addressing challenges like climate change, pandemics, and fundamental physics experiments that require resources and expertise from multiple nations. Large-scale scientific instruments, such as particle accelerators like the Large Hadron Collider, radio telescopes like the Atacama Large Millimeter Submillimeter Array, ALMA, and gravitational wave observatories like LIGO, exemplify this collaborative effort, pushing the frontiers of knowledge by enabling observations and experiments that would be impossible for individual institutions or nations to undertake alone. The ethical considerations surrounding scientific research have also become increasingly prominent, particularly in fields like biotechnology, artificial intelligence, and climate intervention, prompting extensive discussions about responsible innovation, societal impact, and the moral implications of new discoveries. Bioethics, for instance, grapples with issues such as genetic engineering, cloning, and reproductive technologies, ensuring that scientific advancements are pursued in a manner that respects human dignity and societal values. The communication of scientific findings to the public is another vital aspect, as scientific literacy empowers individuals to make informed decisions about health, environment, and technology, bridging the gap between specialized knowledge and everyday life. Science popularizers and educators play a crucial role in translating complex scientific concepts into accessible language, inspiring new generations of scientists and fostering a deeper appreciation for the wonders of the natural world. From the microscopic dance of quarks within a proton to the majestic sweep of galaxies across the cosmic web, science continues its relentless quest to unravel the universe's deepest secrets, driven by an inherent human curiosity and the systematic pursuit of knowledge. Each experiment, each observation, each theoretical model contributes another thread to the intricate tapestry of understanding, revealing the fundamental laws that govern reality and the astonishing complexity of life itself. This ongoing journey, characterized by both meticulous detail and grand conceptual leaps, continuously expands the horizons of human comprehension, transforming the unknown into the understood with a gentle, persistent inquiry that resonates with the profound and intricate harmonies discovered throughout all existence. The profound elegance of scientific inquiry extends far beyond the initial observation, delving into the meticulous process of hypothesis formation, where an educated guess, often rooted in prior knowledge and logical deduction, proposes a potential explanation for a natural phenomenon, setting the stage for empirical investigation. This hypothesis, a testable prediction, then guides the design of experiments, carefully constructed scenarios intended to isolate variables and measure their effects, thereby providing objective data that can either support or refute the initial proposition. The rigorous adherence to experimental controls, ensuring that only the independent variable is altered while all other conditions remain constant, is paramount to establishing causality rather than mere correlation, preventing misinterpretations of observed outcomes. Reproducibility, a cornerstone of scientific validity, demands that any experiment, when repeated under identical conditions by different researchers, should yield consistent results, reinforcing the reliability and robustness of the findings across the global scientific community. As data accumulates from repeated experiments and diverse observations, scientists engage in sophisticated statistical analysis, employing mathematical tools to discern patterns, evaluate the significance of their findings, and quantify the probability that observed effects are not merely due to random chance, thereby strengthening the empirical basis of their conclusions. The peer review process, a critical self-correcting mechanism within science, involves submitting research papers to other experts in the field who scrutinize the methodology, results, and interpretations for flaws, biases, or errors, ensuring that only high-quality, rigorously vetted research enters the public domain. This communal validation is essential for building a collective body of reliable knowledge, where each new discovery is carefully integrated into the existing framework of understanding, continuously refining and expanding our collective scientific worldview. The development of scientific theories represents a higher level of understanding than a mere hypothesis, as a theory is a comprehensive, well-substantiated explanation of some aspect of the natural world, supported by a vast body of evidence from numerous experiments and observations, and capable of making accurate predictions about future phenomena. For instance, the theory of evolution by natural selection, proposed by Charles Darwin and Alfred Russel Wallace, provides a unifying framework for understanding the diversity of life on Earth, explaining how species change over time through genetic variation, inheritance, and differential survival and reproduction in response to environmental pressures. This theory is not merely a guess, but a robust explanation supported by evidence from genetics, paleontology, comparative anatomy, embryology, and biogeography, demonstrating its explanatory power across multiple biological disciplines. Similarly, the theory of plate tectonics revolutionized geology, explaining the movement of Earth's lithospheric plates, the occurrence of earthquakes and volcanic activity, the formation of mountain ranges, and the distribution of continents and oceans over geological timescales. This theory emerged from decades of accumulating evidence, including the mapping of the seafloor, the discovery of magnetic striping patterns on the ocean floor, and the precise measurement of continental drift, all converging to paint a coherent picture of a dynamic, ever-changing planet. The scientific method, therefore, is not a rigid, linear checklist, but rather an iterative, cyclical process of observation, hypothesis, experimentation, analysis, and refinement, constantly building upon previous knowledge and adapting to new evidence. The history of science is replete with paradigm shifts, as described by Thomas Kuhn, where established scientific theories are occasionally overturned or dramatically altered by new evidence that cannot be reconciled with the old framework, leading to revolutionary changes in scientific thought. For example, the Copernican revolution shifted the astronomical paradigm from a geocentric model, where Earth was believed to be the center of the universe, to a heliocentric model, placing the Sun at the center of the solar system, fundamentally altering humanity's perception of its place in the cosmos. This shift was not immediately accepted, but gradually gained traction as observational data, particularly from Galileo's telescopic observations of Jupiter's moons and Venus's phases, provided compelling evidence against the Ptolemaic system. Another monumental paradigm shift occurred with Einstein's theories of relativity, which fundamentally reshaped our understanding of space, time, gravity, and the universe at its largest scales, moving beyond Newton's classical mechanics to describe phenomena at very high speeds or in strong gravitational fields. Special relativity, published in 1905, posited that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum is constant for all observers, leading to mind-bending consequences like time dilation and length contraction. General relativity, published in 1915, extended this framework to include gravity, describing it not as a force, but as a curvature of space-time caused by mass and energy, a concept dramatically confirmed by observations such as the bending of starlight around the sun during a solar eclipse. The development of quantum mechanics in the early 20th century represented another profound shift, providing a framework for understanding the behavior of matter and energy at the atomic and subatomic levels, where classical physics breaks down. This theory introduced concepts like wave-particle duality, where particles can exhibit both wave-like and particle-like properties, and quantum entanglement, where two particles become linked in such a way that the state of one instantaneously affects the state of the other, regardless of distance. The probabilistic nature of quantum mechanics, famously encapsulated by Heisenberg's uncertainty principle, which states that one cannot simultaneously know with perfect accuracy both the position and momentum of a particle, challenged deterministic views of the universe, and continues to inspire deep philosophical debate. Beyond these grand theoretical frameworks, scientific progress is also driven by technological innovation, as new instruments and techniques enable unprecedented observations and measurements, pushing the boundaries of what is knowable. The invention of the microscope, for instance, opened up the unseen world of microorganisms, leading to the germ theory of disease and revolutionizing medicine and public health. Similarly, the development of powerful telescopes, from ground-based observatories to space-based instruments like the Hubble Space Telescope and the James Webb Space Telescope, has allowed astronomers to peer deeper into the universe, observing distant galaxies, exoplanets, and the faint echoes of the Big Bang, revealing the vastness and complexity of the cosmos. The advent of computing power has profoundly transformed scientific research across all disciplines, enabling complex simulations, the analysis of massive data sets, and the modeling of intricate systems that would be impossible to tackle manually. Computational biology, for example, uses algorithms and data structures to understand biological systems, from protein folding to genomic sequencing, accelerating drug discovery and our understanding of genetic diseases. Climate modeling, another computationally intensive field, uses supercomputers to simulate Earth's climate system, predicting future climate scenarios and informing policy decisions regarding global warming. The interdisciplinary nature of modern science is increasingly evident, with breakthroughs often occurring at the intersections of traditional fields, as researchers combine insights and methodologies from different domains to address complex problems. Biophysics merges physics and biology to study biological phenomena at a fundamental level, while astrochemistry combines astronomy and chemistry to investigate the composition and reactions of molecules in space. Materials science, drawing from physics, chemistry, and engineering, focuses on designing and discovering new materials with specific properties for technological applications, from semiconductors to superconductors. The scientific community also grapples with ethical considerations, particularly in fields like biotechnology and artificial intelligence, where the potential societal impact of new discoveries and technologies necessitates careful deliberation and public engagement. Genetic engineering, for instance, offers immense promise for treating diseases and improving crops, but also raises questions about unintended consequences, equity of access, and the very definition of human nature. The development of powerful AI systems prompts discussions about algorithmic bias, job displacement, and the long-term implications for human autonomy and control. Science communication plays a vital role in bridging the gap between scientific discoveries and the general public, translating complex concepts into accessible language and fostering an informed citizenry capable of engaging with science-related policy debates. Effective communication helps to combat misinformation, promote scientific literacy, and inspire the next generation of scientists, ensuring that the benefits of scientific progress are widely understood and appreciated. Public engagement with science through museums, popular science books, documentaries, and citizen science initiatives allows individuals to participate directly in the scientific process, contributing to data collection and analysis while deepening their own understanding. The concept of falsifiability, championed by philosopher Karl Popper, is a crucial demarcation criterion for distinguishing scientific theories from non-scientific ones. Asserting that a scientific hypothesis or theory must, in principle, be capable of being proven false by observation or experiment. This means that a truly scientific statement is not one that can explain everything, but one that makes specific predictions which, if not observed, would invalidate the theory, thereby preventing theories from becoming unfalsifiable dogmas. For example, if the theory of gravity predicted that objects would float upwards, and we consistently observed them falling downwards, the theory would be falsified, prompting a revision or rejection. The ongoing search for a theory of everything, a single, comprehensive theoretical framework that would unify all fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, represents one of the grandest challenges in theoretical physics. String theory and loop quantum gravity are two prominent contenders in this quest, each proposing different approaches to reconciling general relativity with quantum mechanics, aiming to provide a deeper, more unified understanding of the universe at its most fundamental level. While still speculative, these theories drive cutting-edge research in mathematics and physics, pushing the boundaries of human conceptualization. The scientific method's application extends beyond the natural sciences into fields like social sciences, where researchers employ empirical methods to study human behavior, societies, and cultures, albeit with additional complexities due to the subjective nature of human experience and the ethical considerations involved in studying human subjects. Economics, sociology, psychology, and anthropology all utilize systematic observation, data collection, statistical analysis, and theoretical modeling to understand social phenomena, from market trends to cultural evolution. The use of randomized controlled trials, for instance, is increasingly common in social science research to evaluate the effectiveness of interventions and policies, mirroring experimental designs in medicine. The iterative nature of scientific progress means that even well-established theories are subject to continuous scrutiny and refinement as new evidence emerges or more precise measurements become possible, leading to incremental improvements in our understanding. For example, while the basic principles of Newtonian mechanics remain valid for everyday phenomena, they have been refined and superseded by Einstein's relativity at very high speeds and by quantum mechanics at very small scales, demonstrating science's capacity for self-correction and progressive refinement. This constant evolution prevents stagnation as our knowledge deepens with each new discovery, ensuring that scientific knowledge remains dynamic and responsive to new information. The scientific enterprise is fundamentally a collaborative endeavor, with researchers from diverse backgrounds and institutions worldwide sharing data, methods, and ideas through conferences, publications, and international collaborations, fostering a global network of knowledge creation. Large-scale projects such as the Human Genome Project, which mapped the entire human genetic code, or the Large Hadron Collider, which investigates fundamental particles, exemplify this collaborative spirit, requiring the coordinated efforts of thousands of scientists and engineers across multiple countries. This global cooperation accelerates discovery and ensures a broader perspective on complex scientific problems. The role of serendipity in scientific discovery, where unexpected findings lead to significant breakthroughs, highlights the importance of open-mindedness and keen observation in research. The discovery of penicillin by Alexander Fleming, who noticed a mold inhibiting bacterial growth on a contaminated petri dish, is a classic example of serendipitous observation leading to a revolutionary medical advance. Such instances underscore that while systematic experimentation is crucial, the ability to recognize the significance of an anomaly or an unforeseen result is equally vital for scientific progress. The ongoing exploration of extremophiles, organisms that thrive in environments previously thought to be uninhabitable, such as deep-sea hydrothermal vents, highly acidic hot springs, or intensely radioactive waste, has expanded our understanding of the limits of life and the potential for life beyond Earth. These discoveries challenge conventional biological assumptions and inform astrobiological research, guiding the search for extraterrestrial life in similarly extreme conditions on other planets and moons within our solar system and beyond. The biochemical adaptations of these organisms offer insights into novel metabolic pathways and resilient biological structures. The development of CRISPR-Cas9 gene editing technology, a revolutionary tool derived from a bacterial immune system, allows scientists to precisely modify DNA sequences in living organisms, offering unprecedented potential for treating genetic diseases, developing new crops, and understanding gene function. This technology exemplifies how fundamental research into seemingly obscure biological mechanisms can lead to transformative applications with profound implications for medicine, agriculture, and our understanding of life itself. The ethical considerations surrounding germline editing and its potential impact on future generations are actively debated within the scientific community and broader society. The quest for sustainable energy solutions, driven by the scientific understanding of climate change and the finite nature of fossil fuels, involves intensive research into renewable energy sources like solar, wind, geothermal, and nuclear fusion. Scientists are developing more efficient photovoltaic cells, designing advanced wind turbine technologies, and exploring the complex physics of plasma confinement to harness the power of fusion, aiming to provide clean, abundant energy for the future. This multidisciplinary effort integrates physics, chemistry, material science, and engineering to address one of humanity's most pressing challenges. The field of neuroscience continues to unravel the mysteries of the brain, using advanced imaging techniques like fMRI and electrophysiology, alongside computational models, to deepen our understanding of neural function, cognition, and the intricate circuits that govern our thoughts and behaviors. The discoveries in this realm hold the promise of new insights into neurodegenerative diseases, mental health conditions, and the fundamental nature of consciousness. As we delve deeper into the brain's mysteries, the potential for applying this knowledge to improve human health becomes increasingly tangible. Each discovery adds another piece to the intricate puzzle of life, pushing the boundaries of what we know, while reminding us of the vast unknowns still waiting to be uncovered. To understand how billions of neurons interact to produce consciousness, memory, emotion, and thought. Research into neuroplasticity, the brain's ability to reorganize itself by forming new neural connections throughout life, offers hope for treating neurological disorders and enhancing cognitive function. The intricate architecture and dynamic processes of the brain represent one of the most complex systems known to science, demanding innovative approaches and interdisciplinary collaboration. The study of cosmology, the scientific study of the origin, evolution, and large-scale structure of the universe, continues to push the boundaries of human knowledge, addressing fundamental questions about the nature of space, time, and existence itself. Observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang, provide crucial evidence for the universe's expansion and its early conditions. The ongoing investigation into dark matter and dark energy, mysterious components that constitute the vast majority of the universe's mass and energy, but do not interact with light, represents a frontier of modern physics, challenging our current understanding of fundamental particles and forces. The scientific method, with its emphasis on empirical evidence, logical reasoning, and peer review, stands as a powerful antidote to superstition and dogma, providing a systematic approach to understanding the natural world that is constantly open to revision and improvement. It fosters a culture of critical thinking, encouraging skepticism towards unsupported claims, and a commitment to evidence-based reasoning, thereby empowering individuals to make informed decisions in an increasingly complex world. This gentle, persistent inquiry, characteristic of the scientific endeavor, continues to illuminate the profound and intricate harmonies discovered throughout all existence, transforming the unknown into the understood with an unwavering dedication to truth. The scientific method, a systematic approach to understanding the natural world, typically begins with observation, where a scientist meticulously notices a phenomenon or an unanswered question that sparks curiosity and demands further investigation. This initial observation often leads to the formulation of a hypothesis, a testable explanation or prediction about the observed phenomenon, which serves as a tentative answer to the research question. To evaluate the validity of this hypothesis, researchers design and conduct experiments, carefully controlling variables to isolate the effect of the specific factor being studied, ensuring that any observed changes can be attributed directly to the manipulated variable. Data collection during these experiments involves precise measurements and systematic recording of results, often employing specialized instruments to enhance accuracy and minimize human error. Following data collection, analysis becomes a crucial step, where statistical methods and other analytical tools are applied to interpret the collected information, revealing patterns, correlations, or significant differences that might support or refute the initial hypothesis. Based on this analysis, a conclusion is drawn, stating whether the experimental results support or contradict the hypothesis, and often suggesting further avenues for research or refinement of the original idea. The development of scientific theories, which are comprehensive explanations of some aspect of the natural world that are supported by a vast body of evidence, represents a higher level of understanding than a mere hypothesis, offering predictive power and coherence across multiple observations and Scientific progress is not a linear march, but rather an iterative process, characterized by constant questioning, revision, and the building upon previous knowledge, where new discoveries often emerge from unexpected observations or the reinterpretation of existing data. The peer review process, a cornerstone of modern scientific practice, involves subjecting research findings to scrutiny by other experts in the same field before publication, ensuring methodological rigor, accuracy, and the intellectual honesty of the work. This collaborative and critical evaluation helps to filter out flawed research, strengthens the credibility of published results, and fosters a collective pursuit of reliable knowledge within the scientific community. The history of science is replete with paradigm shifts, as described by Thomas Kuhn, where established scientific frameworks are overthrown by new theories that offer a more comprehensive or accurate understanding of reality, leading to revolutionary changes in scientific thought. The Copernican revolution, for instance, shifted the prevailing geocentric model of the universe, which placed Earth at its center, to a heliocentric model, where the Earth and other planets orbit the Sun, fundamentally altering humanity's perception of its place in the cosmos. Another profound shift occurred with the advent of quantum mechanics in the early 20th century, which provided a revolutionary description of matter and energy at the atomic and subatomic levels, challenging classical physics' deterministic view and introducing concepts like wave-particle duality and quantum entanglement. The branches of science are incredibly diverse, each specializing in different aspects of the natural world, yet often interconnected and mutually reinforcing in their pursuit of knowledge. Physics, often considered the fundamental science, investigates the basic constituents of the universe: energy, force, space, and time, seeking to understand the fundamental laws that govern all phenomena. Chemistry focuses on the composition, structure, properties, and reactions of matter, exploring how atoms combine to form molecules, and how these molecules interact to create the vast array of substances we observe. Biology, the study of life, encompasses everything from the molecular mechanisms within cells to the complex interactions within ecosystems, unraveling the mysteries of heredity, evolution, and the intricate processes that sustain living organisms. Earth sciences, including geology, meteorology, and oceanography, examine the planet's physical structure, processes, and phenomena, from the formation of mountains to the dynamics of weather patterns and the circulation of ocean currents. Astronomy delves into the celestial objects and phenomena beyond Earth's atmosphere, investigating stars, galaxies, planets, and the origin and evolution of the universe itself. Mathematics, while often considered a separate discipline, serves as an indispensable language and tool for all scientific endeavors, providing the framework for quantitative analysis, modeling, and the precise expression of scientific laws. Statistical methods are crucial for interpreting experimental data, allowing scientists to assess the significance of their findings, quantify uncertainty, and draw reliable conclusions from observations that are often subject to natural variation. Computational science, a rapidly growing field, utilizes powerful computers and algorithms to simulate complex systems, analyze massive data sets, and develop predictive models, enabling research that would be impossible through traditional experimental or theoretical approaches alone. The application of scientific knowledge through technology has profoundly transformed human civilization, leading to innovations that have reshaped daily life, medicine, communication, and industry. The development of vaccines, rooted in microbiology and immunology, has eradicated or significantly reduced the incidence of numerous infectious diseases, saving countless lives and improving global public health. The invention of the transistor, a product of solid-state physics, laid the foundation for modern electronics, leading to computers, smartphones, and the internet, which have revolutionized communication and information access worldwide. Agricultural science has dramatically increased food production through advancements in crop breeding, pest control, and soil management, supporting a growing global population. Material science, an interdisciplinary field, designs and discovers new materials with specific properties, leading to innovations in everything from aerospace engineering to biomedical implants. Ethical considerations are paramount in scientific research, guiding scientists to conduct their work responsibly, with integrity and with due regard to the well-being of humans, animals, and the environment. Bioethics, for example, addresses the moral implications of advances in biology and medicine, such as genetic engineering, cloning, and artificial intelligence, prompting careful deliberation about the potential benefits and risks of these powerful technologies. Environmental ethics guides research into climate change, conservation, and pollution, urging scientists to consider the long-term impacts of human activities on the planet's ecosystems and biodiversity. The responsible conduct of research also includes principles of honesty in reporting results, avoiding plagiarism, and ensuring the fair treatment of research participants, upholding the public trust in scientific findings. The process of scientific discovery often involves serendipity, where unexpected findings or accidental observations lead to significant breakthroughs, demonstrating that preparedness and an open mind are as important as rigorous planning. The discovery of penicillin by Alexander Fleming, for instance, resulted from a contaminated petri dish where mold inhibited bacterial growth, an observation that he astutely recognized as potentially significant, leading to the development of the first antibiotic and revolutionizing medicine. Similarly, the cosmic microwave background radiation, a crucial piece of evidence supporting the Big Bang theory, was accidentally detected by Arno Penzias and Robert Wilson as persistent background noise in their antenna, which they initially struggled to eliminate before realizing its profound cosmological implications. Science education plays a vital role in fostering scientific literacy within the general public, enabling individuals to understand scientific concepts, evaluate scientific claims, and engage in informed discussions about science-related issues that affect society. Encouraging critical thinking skills from an early age, science education helps individuals distinguish between evidence-based information and pseudoscience, promoting a more rational and analytical approach to understanding the world. Public engagement with science, through museums, documentaries, and citizen science initiatives, further democratizes scientific knowledge, allowing broader participation in research and increasing appreciation for the scientific endeavor. The funding of scientific research is a complex ecosystem involving government agencies, private foundations, universities, and corporations, each with different priorities and mechanisms for supporting scientific inquiry. Government grants, often awarded through competitive peer-reviewed processes, typically support basic research that expands fundamental knowledge with long-term societal benefits that may not be immediately apparent. Private foundations often focus on specific areas of research, such as disease prevention or environmental conservation, providing targeted funding to address particular societal challenges. Corporate research and development departments primarily invest in applied research, aiming to develop new products or processes that have commercial value, bridging the gap between scientific discovery and technological innovation. International collaboration is increasingly important in addressing global scientific challenges, such as climate change, pandemics, and space exploration, where shared resources, diverse expertise, and coordinated efforts are essential for progress. Large-scale projects like the Large Hadron Collider, operated by CERN, involve thousands of scientists and engineers from around the world, working together to explore the fundamental nature of matter and energy, demonstrating the power of collective scientific endeavor. The Intergovernmental Panel on Climate Change, IPCC, synthesizes climate research from scientists globally, providing comprehensive assessments of climate change and its impacts, informing international policy decisions. The scientific community is a vibrant and diverse group of individuals from all backgrounds and cultures, united by a shared passion for understanding the natural world and a commitment to the principles of scientific inquiry. This diversity of perspectives and experiences enriches scientific discourse, fosters creativity, and helps to challenge existing assumptions, leading to more robust and inclusive scientific understanding. Mentorship plays a critical role in training the next generation of scientists, passing down not only technical skills and knowledge, but also the ethical standards and intellectual curiosity that define the scientific profession. The pursuit of scientific knowledge is an inherently human endeavor, driven by an innate curiosity to explore the unknown, to unravel the mysteries of the universe, and to improve the human condition through deeper understanding. From the earliest astronomical observations by ancient civilizations to the most cutting-edge research in quantum computing and genetic engineering, science continuously pushes the boundaries of what is known, expanding the horizons of human comprehension. This relentless quest for truth, characterized by rigorous methodology, open-mindedness, and a willingness to revise understanding in the face of new evidence, continues to be one of humanity's most profound and enduring intellectual achievements. The intricate dance of discovery, where observation leads to hypothesis, experiment to data, and analysis to theory, forms the elegant rhythm of scientific progress, perpetually refining our map of reality. Each new insight, whether a grand theory explaining the cosmos or a subtle detail revealing a molecular interaction, adds another thread to the rich tapestry of scientific knowledge, weaving together a more complete and coherent picture of existence. The beauty of science lies not only in the answers it provides, but also in the questions it continually inspires, propelling humanity forward into ever deeper realms of understanding. The ongoing dialogue between theory and experiment, where predictions are tested and models are refined, ensures that scientific knowledge remains dynamic and self-correcting, constantly evolving towards greater accuracy and explanatory power. This profound journey of exploration, driven by an insatiable desire to comprehend the universe in all its complexity and wonder, remains a testament to the enduring power of human intellect and curiosity. The profound journey of exploration, driven by an insatiable desire to comprehend the universe in all its complexity and wonder, remains a testament to the enduring power of human intellect and curiosity. This intellectual odyssey, which began with humanity's earliest attempts to make sense of the natural world, has continuously unfolded through distinct historical periods, each characterized by unique methodologies, prevailing paradigms, and groundbreaking discoveries that collectively form the intricate tapestry of scientific progress. From the observational astronomy of ancient civilizations, meticulously charting celestial movements to predict seasons and navigate vast oceans, to the sophisticated particle accelerators probing the fundamental constituents of matter, science has consistently pushed the boundaries of human perception and understanding, revealing layers of reality previously unimaginable. Consider the foundational contributions of ancient Greek thinkers, who, while often relying on philosophical reasoning rather than empirical experimentation in the modern sense, laid crucial groundwork by emphasizing logic, mathematics, and systematic observation in their inquiries into the cosmos and the natural world. Thinkers like Thales of Miletus, often considered the first philosopher and scientist, proposed that water was the fundamental element from which everything originated, attempting to explain natural phenomena through natural causes rather than supernatural intervention, a radical departure from mythological explanations prevalent at the time. Anaximander, his student, further developed these ideas, suggesting an infinite, undefined primary substance called the aperon, and theorizing about the evolution of species from aquatic forms, demonstrating an early inclination towards naturalistic explanations for life's diversity. Pythagoras and his followers deeply explored the mathematical relationships underlying musical harmony and geometric forms, believing that numbers held the key to understanding the universe, a concept that resonates even today in the mathematical language of physics. Euclid's Elements, a monumental work of geometry, established an axiomatic deductive system that served as a model for rigorous scientific thought for over 2 millennia, demonstrating how complex truths could be derived from a few self-evident postulates. Aristotle, a towering figure whose influence permeated Western thought for centuries, engaged in extensive biological classification, meticulous observation of animal life, and systematic cataloging of natural phenomena, developing a comprehensive system of logic and an empirical approach that, despite its limitations, represented a significant advancement in systematic inquiry. His theories on motion, while later superseded, provided the dominant framework for understanding the physical world for centuries, emphasizing teleology, the idea that natural processes are guided by inherent purposes, which shape subsequent scientific discourse. Following the classical period, the Islamic Golden Age, spanning roughly from the 8th to the 14th centuries, witnessed an extraordinary flourishing of scientific inquiry, preserving and expanding upon Greek knowledge while introducing novel methodologies and discoveries. Scholars in centers like Baghdad, Cairo, and Cordoba translated and meticulously studied ancient texts, but critically, they also innovated, emphasizing experimental methods and empirical observation to a degree unprecedented in the ancient world. Figures such as Ibn al-Haytham, known in the West as Alhazen, revolutionized optics through rigorous experimentation, demonstrating that vision occurs when light enters the eye, rather than emanating from it, and accurately describing the anatomy of the eye, refraction, and reflection, laying the groundwork for modern optical science. His methodical approach, involving hypothesis testing and controlled experiments, is often cited as an early example of the scientific method. Al-Biruni, a polymath of the 11th century, made significant contributions to astronomy, mathematics, geography, and physics, calculating the radius of the Earth with remarkable accuracy using a sophisticated trigonometric method, and theorizing about the Earth's rotation on its axis, anticipating later European discoveries. He also engaged in comparative studies of cultures and religions, demonstrating a broad intellectual curiosity that transcended disciplinary boundaries. Avicenna, a Persian polymath, authored the Canon of Medicine, a comprehensive medical encyclopedia that synthesized Greek and Islamic medical knowledge, becoming a standard textbook in Europe and the Islamic world for centuries, meticulously describing diseases, their symptoms, and treatments, and emphasizing clinical observation and experimentation. These scholars not only preserved ancient knowledge, but actively advanced it, developing new instruments like the astrolabe, refining astronomical tables, and establishing hospitals that incorporated systematic clinical observation and pharmaceutical advancements, demonstrating a practical application of scientific understanding for societal benefit. The Renaissance and the subsequent scientific revolution in Europe marked a profound paradigm shift, fundamentally altering humanity's understanding of the universe and its place within it, moving away from Aristotelian dogma and theological explanations towards empirical observation, mathematical reasoning, and mechanical philosophy. Nicolaus Copernicus ignited this revolution with his heliocentric model of the solar system, proposing that the Earth and other planets orbited the Sun, a radical departure from the geocentric Ptolemaic system that had dominated thought for over 1,400 years, challenging deeply ingrained religious and philosophical beliefs. Galileo Galilei, often considered the father of observational astronomy and modern physics, utilized the newly invented telescope to gather empirical evidence supporting the Copernican model, observing the phases of Venus, the moons of Jupiter, and sunspots, which directly contradicted Aristotelian cosmology and provided compelling visual proof of a dynamic, non-Earth-centered universe. His experiments on falling objects also challenged Aristotelian physics, demonstrating that objects fall at the same rate regardless of their mass, laying the groundwork for classical mechanics through meticulous measurement and mathematical analysis. Johannes Kepler, building upon Tycho Brahe's precise astronomical observations, formulated his 3 laws of planetary motion, describing elliptical orbits and the mathematical relationships governing planetary speeds, providing a precise mathematical description of celestial mechanics that further solidified the heliocentric view. Isaac Newton, synthesizing the work of his predecessors, developed classical mechanics with his 3 laws of motion and the law of universal gravitation, explaining both terrestrial and celestial phenomena with a single elegant mathematical framework, demonstrating that the same physical laws apply throughout the universe, a monumental achievement that unified disparate observations into a coherent, predictive theory. Newton also developed calculus, a powerful mathematical tool essential for describing continuous change, which became indispensable for physics and engineering, fundamentally transforming the language of science. The Enlightenment period further propelled scientific inquiry, emphasizing reason, individualism, and the systematic application of scientific methods to all aspects of knowledge, including human society and governance. Carl Linnaeus developed a hierarchical system for classifying organisms, known as binomial nomenclature, which provided a standardized, universally accepted method for naming and organizing the vast diversity of life, laying the foundation for modern taxonomy and systematics. Antoine Lavoisier, through meticulous quantitative experiments, established the law of conservation of mass in chemical reactions, demonstrated the role of oxygen in combustion and respiration, and helped dismantle the phlogiston theory, fundamentally transforming chemistry into a quantitative science and earning him the title of the father of modern chemistry. His precise measurements and systematic approach set new standards for chemical experimentation. James Watt's improvements to the steam engine provided a powerful, efficient source of mechanical energy, driving the Industrial Revolution and profoundly transforming manufacturing, transportation, and society, demonstrating the practical impact of scientific and engineering innovation. Alessandro Volta invented the voltaic pile, the first true electrical battery, providing a continuous source of electric current and opening up new avenues for research into electricity and magnetism, leading to subsequent discoveries by Ørsted, Ampere, and Faraday. Edward Jenner developed the smallpox vaccine, building upon folk knowledge and systematic observation, initiating the field of immunology, and demonstrating the immense potential of scientific medicine to prevent disease on a global scale, a triumph of empirical public health. The 19th century witnessed an explosion of scientific discovery across numerous fields, characterized by the development of unifying theories and the emergence of specialized disciplines. John Dalton proposed the atomic theory, positing that matter is composed of indivisible atoms of specific weights, providing a quantitative basis for understanding chemical reactions and laying the foundation for modern chemistry, reviving an ancient Greek idea with empirical support. Michael Faraday's groundbreaking experiments in electromagnetism demonstrated the interrelationship between electricity and magnetism, leading to the invention of the electric motor and generator, and laying the empirical groundwork for James Clerk Maxwell's unified theory of electromagnetism, which described light as an electromagnetic wave, a monumental synthesis of physics. Charles Darwin, through extensive observation during his voyage on the HMS Beagle and meticulous compilation of evidence, developed the theory of evolution by natural selection, explaining the diversity of life and its adaptation to environments, fundamentally transforming biology and challenging prevailing creationist views, providing a powerful, unifying explanation for the history of life on Earth. Louis Pasteur's experiments disproved spontaneous generation and established the germ theory of disease, demonstrating that microorganisms cause fermentation and disease, leading to pasteurization, vaccines for rabies and anthrax, and revolutionary advancements in public health and medicine, saving countless lives. Gregor Mendel, working in relative obscurity, conducted meticulous experiments with pea plants, elucidating the fundamental laws of heredity, segregation, and independent assortment, laying the foundation for modern genetics, though his work was only recognized decades later. Dmitry Mendeleev organized the known chemical elements into the periodic table based on their atomic weights and recurring chemical properties, remarkably predicting the existence and properties of undiscovered elements, providing a powerful framework for understanding chemical behavior and guiding future research. The turn of the 20th century ushered in a new era of physics, challenging classical notions of space, time, and matter, and leading to revolutionary insights into the fundamental nature of reality. Max Planck introduced the concept of energy quantization, proposing that energy is emitted and absorbed in discrete packets called quanta, a radical idea that initiated quantum mechanics and explained phenomena like blackbody radiation, marking a fundamental departure from classical physics. Albert Einstein, in his miracle year of 1905, published 4 seminal papers, including his theory of special relativity, which redefined space and time as relative to the observer, and established the equivalence of mass and energy, E equals mc squared, profoundly altering our understanding of the universe, and his explanation of the photoelectric effect using Planck's quantum hypothesis, further solidifying the quantum revolution. Later, his theory of general relativity, published in 1915, extended special relativity to include gravity, describing it as the curvature of space-time caused by mass and energy, providing a new framework for understanding the universe on cosmological scales and predicting phenomena like gravitational lensing and black holes. Ernest Rutherford's gold foil experiment revealed the atomic nucleus, demonstrating that atoms consist mostly of empty space with a dense, positively charged core, overturning the prevailing plum pudding model and paving the way for the modern understanding of atomic structure. Niels Bohr developed a quantum model of the atom, explaining the stability of electron orbits and the emission of discrete spectral lines, further integrating quantum concepts into atomic theory. The development of quantum mechanics by Schrödinger, Heisenberg, and Dirac provided a comprehensive mathematical framework for understanding the behavior of matter and energy at the atomic and subatomic levels, leading to technologies like lasers, transistors, and nuclear energy, fundamentally transforming modern technology. The mid-20th century saw spectacular advancements in molecular biology and genetics, unraveling the mysteries of life itself. Oswald Avery's experiments in the 1940s demonstrated that DNA, not protein, was the carrier of genetic information, a crucial insight that set the stage for later discoveries. James Watson and Francis Crick, building upon the X-ray diffraction work of Rosalind Franklin and Maurice Wilkins, elucidated the double helix structure of DNA in 1953, revealing how genetic information is encoded and replicated, a discovery that revolutionized biology and opened the door to understanding heredity, disease, and evolution at a molecular level. This breakthrough led to the cracking of the genetic code, the development of recombinant DNA technology, and ultimately the Human Genome Project, which mapped the entire human genetic blueprint, providing unprecedented insights into human biology, health, and disease susceptibility. The discovery of pulsars by Jocelyn Bell Burnell and Anthony Hewish in 1967 provided observational evidence for neutron stars, exotic remnants of massive stellar explosions, further expanding our understanding of extreme astrophysical phenomena. The development of plate tectonics theory in the 1960s, synthesizing decades of geological and geophysical observations, explained the movement of continents, the formation of mountains, earthquakes, and volcanic activity, providing a unifying framework for understanding Earth's dynamic geological processes. The late 20th and early 21st centuries have been characterized by increasing interdisciplinarity, the rise of computational science, and the exploration of complex systems. The advent of powerful supercomputers and advanced algorithms has enabled scientists to simulate complex phenomena, from climate change models to protein folding, providing insights that would be impossible through traditional experimental or analytical methods. The development of the World Wide Web, initially conceived at CERN for sharing scientific data, revolutionized information exchange and collaboration among scientists globally, accelerating the pace of discovery. The discovery of the Higgs boson at CERN's Large Hadron Collider in 2012 confirmed a fundamental particle predicted by the Standard Model of particle physics, completing our current understanding of the fundamental forces and particles that constitute the universe, a monumental achievement in experimental physics. The detection of gravitational waves by the LIGO experiment in 2015, nearly a century after Einstein predicted their existence, opened a new window onto the universe, allowing us to observe violent cosmic events like black hole mergers and neutron-star collisions, providing a novel way to probe the cosmos beyond electromagnetic radiation. Advances in neuroscience, fueled by sophisticated imaging techniques like fMRI and optogenetics, are beginning to unravel the intricate workings of the human brain, providing insights into consciousness, memory, and neurological disorders, pushing the boundaries of our understanding of ourselves. The field of material science has engineered novel materials with unprecedented properties, from superconductors and graphene to self-healing polymers, driving innovation in electronics, energy, and medicine. Biotechnology continues to advance rapidly, with CRISPR-Cas9 gene editing technology offering unprecedented precision in modifying DNA, holding immense promise for treating genetic diseases and engineering new biological functions, while also raising profound ethical considerations. Environmental science has emerged as a critical discipline, integrating knowledge from biology, chemistry, physics, geology, and social sciences to understand and address pressing global challenges such as climate change, biodiversity loss, and pollution, providing the scientific basis for sustainable practices and policy decisions. The ongoing exploration of Mars and other celestial bodies through robotic missions continues to yield data that informs our understanding of planetary formation, the potential for extraterrestrial life, and the history of our own solar system, pushing the boundaries of astrobiology and planetary science. The development of artificial intelligence and machine learning is not only transforming technology, but also becoming a powerful tool for scientific discovery, accelerating data analysis, hypothesis generation, and experimental design across virtually all scientific disciplines, from drug discovery to materials design. The concept of citizen science, where the public participates in scientific research, from classifying galaxies to monitoring local ecosystems, has expanded the reach and capacity of scientific data collection, fostering a greater public engagement with scientific inquiry. The constant refinement of measurement techniques, from atomic clocks that measure time with extraordinary precision to electron microscopes that visualize individual atoms, continues to push the limits of what can be observed and understood, revealing ever finer details of the natural world. Throughout this grand narrative, the scientific method remains the bedrock of progress, a systematic approach to inquiry that involves observation, hypothesis formulation, experimentation, data analysis, and peer review, ensuring rigor and reliability in the pursuit of knowledge. This iterative process, where theories are constantly tested, refined, or even overturned by new evidence, embodies the self-correcting nature of science, distinguishing it from other forms of knowledge. The scientific community, a global network of researchers, collaborates and competes, sharing findings through publications and conferences, fostering a dynamic environment where ideas are challenged and built upon, collectively advancing the frontiers of understanding. The ethical considerations inherent in scientific research, particularly in fields like genetics, artificial intelligence, and nuclear technology, are increasingly recognized as integral to responsible scientific practice. prompting ongoing societal dialogues about the implications and applications of new discoveries. The pursuit of science is not merely an accumulation of facts, but a continuous quest for deeper explanations, for unifying principles that connect seemingly disparate phenomena, and for a more profound comprehension of the intricate workings of the cosmos and the delicate balance of life within it. This enduring human endeavor, characterized by relentless curiosity, rigorous skepticism, and a profound appreciation for the beauty and order of the natural world, continues to illuminate our path, expanding the horizons of human knowledge and shaping our collective future with its transformative power. This enduring human endeavor, characterized by relentless curiosity, rigorous skepticism, and a profound appreciation for the beauty and order of the natural world, continues to illuminate our path, expanding the horizons of human knowledge and shaping our collective future with its transformative power. As the tapestry of scientific understanding unfolds, we recognize that its threads are woven from countless individual discoveries and the cumulative efforts of generations, each building upon the insights of those who came before, creating an ever more intricate and robust picture of reality. Consider the foundational shift from geocentric to heliocentric models of the solar system, a monumental intellectual leap initiated by Nicolaus Copernicus, who, through meticulous astronomical observations and mathematical reasoning, proposed that the Earth and other planets orbited the Sun, thereby challenging deeply entrenched philosophical and theological doctrines of his era. This revolutionary idea, initially met with resistance, was subsequently refined and powerfully supported by Johannes Kepler's laws of planetary motion, which precisely described elliptical orbits and the varying speeds of planets, derived from Tycho Brahe's extensive and remarkably accurate naked-eye observations, providing empirical evidence that solidified the heliocentric view. Galileo Galilei, with his pioneering use of the telescope, offered further compelling visual proof, observing the phases of Venus, the moons of Jupiter, and the mountainous surface of the Moon, observations that directly contradicted the prevailing Aristotelian cosmology and irrevocably altered humanity's perception of its place in the universe. The scientific method itself, a cornerstone of modern inquiry, evolved over centuries, formalizing the process of observation, hypothesis formation, experimentation, data analysis, and conclusion, providing a systematic framework for investigating natural phenomena and distinguishing reliable knowledge from speculation. Francis Bacon, a prominent figure in the 17th century, advocated for an empirical approach, emphasizing inductive reasoning and the systematic collection of data to draw general conclusions, thereby moving away from purely deductive, logic-based arguments that often relied on untested assumptions. René Descartes, while emphasizing rational deduction, also contributed to the scientific method by advocating for clear and distinct ideas, rigorous doubt, and the breaking down of complex problems into simpler components, laying groundwork for analytical thinking. The Royal Society of London, established in 1660, played a crucial role in promoting experimental science, fostering collaboration among natural philosophers, and disseminating findings through publications like Philosophical Transactions, thereby establishing a culture of open inquiry and peer review. Isaac Newton, a towering figure of the scientific revolution, synthesized the work of his predecessors into a grand unified theory of mechanics and gravitation, demonstrating that the same laws governing the fall of an apple on Earth also dictated the orbits of planets, thereby establishing a universal framework for understanding motion and force. His Principia Mathematica, published in 1687, introduced calculus as a powerful mathematical tool for describing continuous change, providing the language necessary to articulate physical laws with unprecedented precision, and enabling predictions that could be rigorously tested against observation. Newton's laws of motion, inertia, force equals mass times acceleration, and action-reaction became the bedrock of classical physics, explaining everything from projectile trajectories to the tides, and remained unchallenged as the definitive description of the physical world for over 2 centuries. The concept of universal gravitation, positing an attractive force between any 2 objects with mass, proportional to their masses and inversely proportional to the square of the distance between them, revolutionized astronomy and provided a coherent explanation for the structure and dynamics of the solar system. The 18th and 19th centuries witnessed an explosion of scientific inquiry across diverse fields, driven by both intellectual curiosity and practical applications, leading to profound insights into the nature of matter, energy, and life. Antoine Lavoisier, through meticulous quantitative experiments, established the law of conservation of mass, demonstrating that matter is neither created nor destroyed in chemical reactions, fundamentally transforming chemistry from an alchemical art into a rigorous quantitative science. John Dalton's atomic theory, proposed in the early 19th century, posited that all matter is composed of indivisible particles called atoms, each element having atoms of a unique mass, and that chemical reactions involve the rearrangement of these atoms, providing a powerful conceptual framework for understanding chemical phenomena. Michael Faraday's groundbreaking experiments in electromagnetism revealed the intricate connection between electricity and magnetism, demonstrating that a changing magnetic field can induce an electric current and vice versa, laying the empirical foundation for modern electrical engineering and technology. James Clerk Maxwell later synthesized these observations into a unified theory of electromagnetism, encapsulated in his famous equations, which predicted the existence of electromagnetic waves traveling at the speed of light, thereby unifying electricity, magnetism, and light into a single theoretical framework. The development of thermodynamics in the 19th century, through the work of scientists like Sadi Carnot, Rudolf Clausius, and Lord Kelvin, established fundamental laws governing energy transformations, including the conservation of energy, the first law, and the concept of entropy, the second law, which describes the irreversible tendency of systems to move towards greater disorder. These laws provided a deep understanding of heat engines, refrigerators, and the ultimate fate of the universe, demonstrating that energy cannot be created or destroyed, but its quality or usefulness tends to degrade over time. Simultaneously, the burgeoning field of biology experienced its own revolution with Charles Darwin's theory of evolution by natural selection, presented in On the Origin of Species in 1859, which proposed that all life forms share a common ancestry and have diversified over vast spans of time through a process where advantageous traits are preferentially passed on to successive generations. This theory, supported by a wealth of evidence from geology, paleontology, comparative anatomy, and embryology, provided a powerful and elegant explanation for the diversity and adaptation of life on Earth, fundamentally altering humanity's understanding of its biological origins and its relationship to other species. The late 19th and early 20th centuries ushered in a new era of physics, challenging classical notions of space, time, matter, and energy, leading to the development of relativity and quantum mechanics. Albert Einstein's theories of special and general relativity revolutionized our understanding of gravity, space, and time, demonstrating that space and time are not absolute, but are interwoven into a flexible fabric called spacetime, which is curved by the presence of mass and energy. Special relativity, introduced in 1905, showed that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum is constant for all observers, leading to profound consequences such as time dilation and length contraction. General relativity, published in 1915, extended these ideas to include gravity, describing it not as a force, but as a manifestation of the curvature of spacetime, providing a more accurate description of gravity than Newton's theory, and successfully predicting phenomena like the bending of light by massive objects and the existence of black holes. Concurrently, the exploration of the atomic and subatomic realms gave rise to quantum mechanics, a radically new framework for understanding the behavior of matter and energy at the smallest scales, where classical physics breaks down. Max Planck's introduction of energy quantization in 1900, proposing that energy is emitted or absorbed in discrete packets called quanta, marked the beginning of quantum theory, explaining the spectrum of black body radiation. Niels Bohr's model of the atom, which proposed that electrons orbit the nucleus in specific energy levels and can jump between these levels by absorbing or emitting quanta of light, successfully explained the discrete spectral lines observed in atomic emissions. Louis de Broglie's hypothesis of wave-particle duality, suggesting that particles like electrons can also exhibit wave-like properties, and Erwin Schrödinger's wave equation, which describes the probability of finding a particle at a given location, further solidified the quantum mechanical view. Werner Heisenberg's uncertainty principle, stating that certain pairs of physical properties, like position and momentum, cannot both be known with arbitrary precision simultaneously, highlighted the inherent probabilistic nature of the quantum world, fundamentally altering our deterministic view of reality. The 20th century also witnessed monumental advancements in biology, particularly with the elucidation of the structure and function of DNA, the molecule of heredity. Oswald Avery, Colin MacLeod, and Macklin McCarty's experiments in the 1940s provided compelling evidence that DNA, not protein, was the genetic material responsible for transmitting hereditary information, a finding that profoundly reshaped the field of genetics. James Watson and Francis Crick, building upon the X-ray diffraction data generated by Rosalind Franklin and Maurice Wilkins, famously deduced the double helix structure of DNA in 1953, revealing how genetic information is encoded in the sequence of nucleotide bases and how it can be accurately replicated, thereby providing the molecular basis for inheritance and evolution. This discovery launched the era of molecular biology, leading to breakthroughs in genetic engineering, gene therapy, and the ambitious Human Genome Project, which successfully mapped the entire human genetic code, opening new avenues for understanding disease, development, and human variation. The field of cosmology, the study of the origin and evolution of the universe, has also undergone dramatic transformations, moving from philosophical speculation to a rigorous scientific discipline supported by observational evidence. Edwin Hubble's observations in the 1920s, demonstrating that distant galaxies are receding from us and that the universe is expanding, provided the first strong empirical evidence for the Big Bang Theory, which posits that the universe originated from an extremely hot, dense state approximately 13.8 billion years ago. The discovery of the cosmic microwave background radiation in 1964 by Arno Penzias and Robert Wilson, a faint echo of the Big Bang, provided further compelling evidence for this model, confirming predictions made by George Gamow and others. Subsequent observations, including those from the Hubble Space Telescope and the Wilkinson Microwave Anisotropy Probe, have refined our understanding of the universe's age, composition, and expansion rate, revealing that it is predominantly composed of mysterious dark matter and dark energy, which continue to be subjects of intense scientific investigation. Beyond the fundamental sciences, the application of scientific principles has led to transformative technological advancements that have reshaped human society, from the development of antibiotics and vaccines that have dramatically extended human lifespans, to the invention of computers and the internet that have revolutionized communication and information access. The understanding of semiconductor physics, for example, led to the invention of the transistor in the mid-20th century, a tiny electronic switch that formed the basis of all modern electronics, enabling the miniaturization and proliferation of computing devices. The development of medical imaging techniques, such as X-rays, MRI, and CT scans, has revolutionized diagnostics, allowing physicians to visualize the internal structures of the human body with unprecedented clarity, leading to earlier and more effective treatments. The ongoing quest for sustainable energy solutions, driven by scientific understanding of thermodynamics and material science, seeks to harness renewable resources like solar, wind, and geothermal energy to mitigate climate change and ensure a stable energy future for humanity. The interdisciplinary nature of modern science is increasingly evident, with breakthroughs often occurring at the intersections of traditional fields, such as in bioinformatics, which combines computer science and biology to analyze vast amounts of biological data, or in nanotechnology, which manipulates matter at the atomic and molecular scale to create novel materials and devices. The study of complex systems, ranging from ecological networks to the human brain, requires integrating insights from physics, biology, computer science, and mathematics, highlighting the interconnectedness of all scientific endeavors. This collaborative spirit, characterized by the sharing of data, methodologies, and ideas across national and disciplinary boundaries, accelerates the pace of discovery and fosters a more holistic understanding of the natural world. The scientific process is inherently self-correcting, constantly refining its models and theories in light of new evidence, embracing skepticism as a virtue, and recognizing that current understanding is always provisional and subject to revision. This commitment to empirical validation and logical coherence distinguishes science from other forms of knowledge, ensuring its reliability and its capacity for continuous progress. The beauty of science lies not only in the profound truths it uncovers, but also in the elegant simplicity of its underlying principles, the intricate complexity of the phenomena it describes, and the boundless potential it offers for addressing humanity's greatest challenges and enriching our collective existence. It is a journey of perpetual discovery, an endless exploration of the unknown, driven by the innate human desire to comprehend the universe and our place within its grand, unfolding narrative.